Okay, well, good morning, everyone. Welcome to our theory day, and it's a great pleasure to start off with Wayne, who's going to be telling us what we've learned from Planck.
I thank the organizers for this opportunity to speak. I'm not quite sure I thank the organizers for the title of the talk. It left me scratching my head a bit, and I think for the number of questions I got from you guys about what exactly I'm going to talk about, I think it left you scratching your heads a little bit too, because there's nothing I can really add to the beautiful talks we've already heard on Monday. So one thing is that you can tell right off that the title of the talk was written by the organizers, because I'm not from this side of the pond. So learned, not learned. and we, I think that was meant to be we as the community outside of Planck, but I'm going to take this is a more modest goal and say what I learned from Planck, or a reinterpretation that maybe they meant the royal we and it was aggrandizing, but I'll take the more modest standpoint. And to cut to the chase, depending on the day you ask me, I would give you different responses to this. So on every other day, I would say, well, it's how I learned to strange love tension, or maybe it's anomalies, or maybe it's curiosities. And sometimes I feel like this guy riding the thing down to the crash. Hope you recognize that reference. And other days I would say, look at this brilliant data. What this tells us is that we should stop worrying and love lambda CDM. So I'm going to start from the end and end at the beginning, and first tell you again what beautiful data this is and how remarkably effective the lambda CDM model is, and why when we're chasing these anomalies, which is of course fun, and I'm going to take you down a path that is a recent path about thinking about dark components at the epoch of matter radiation equality to see what we would need to do to resolve Hubble tension. Really, it's slim pickings. So so far, I don't see a compelling theory that takes all these anomalies, puts them together, and either explains multiple ones or makes predictions. And that's what we have to see to make this more than a curiosity of chasing tensions. Okay. So review from Monday, of course. So Planck is the paradigm now of precision cosmology, giving us, for cosmology, these three beautiful maps of temperature, polarization, and lensing, and also the legacy for both galactic and extragalactic astrophysics with the maps over the 9 frequency bands. And probably equally importantly is the control over systematics, most recently in the polarization, to be able to extract the cosmology from polarization. And has led us to this picture where the fluctuations are Gaussian, adiabatic, and beautifully consistent with lambda CDM, at least internally. So what does that mean? It means near perfection. So all of this vast data set is described nearly perfectly by the lambda CDM model, which we all know, is described by only 6 numbers. So all of these things in the internal data set established by all of the microwave background experiments over the last few decades, there we go, is described beautifully by these 6 numbers. They're measured to sub% precision, a little bit worse for tau, and are in beautiful agreement with this exquisitely precise data, and with the control of systematics, I would also say accurate data. Now, they have predictive power as well. So this is one slide that I like from the legacy paper. I think Martin didn't show this on Monday, but it shows you that because the temperature and polarization are correlated, not only is it beautifully consistent with lambda CDM, the residuals are small for the most part, they're also predictive in the sense that temperature and polarization are correlated, so you condition on what you know about the polarization field, you predict what you should see in the polarization, and reduce the sample variance. So all the fluctuations also match to the most part, but there are moderately significant deviations. And these are curiosities. They're expected to sigma-like outliers. But some of them are also in positions which drive some of our cosmological parameters. I'm going to talk a little bit about the TT glitch at 20 to 30, which we've heard about on Monday, and also this anomalous area in the TE spectrum, which is going to be important for the discussion of the Hubble parameter tension and its possible resolutions, especially its possible resolutions. Okay, and then from the going to the external, these 6 numbers that are established by the microwave background, especially Planck, predict all of cosmology now, because in the lambda CDM model there are only 6 parameters, and is again beautifully consistent with most of the data to this sub% level precision, Big Bang Nucleosynthesis for the baryons, and the relative distance ladder of supernovae and BAO, power spectrum, and growth of structure. And yes, I would even say the things that we've been talking about as tensions, if you asked me this 10 years ago, I would say this is beautiful agreement. So all of this, the 6 numbers predict all of the data, including the things we call as tension, to better than 10%. So there's no tension, there's no big anomalous tension that would drive us to say lambda CDM has to be completely revised. If these tensions have some physical explanation at all, it's going to be a very small deviation from lambda CDM. So it's going to be something that you're inserting to tweak the model a little bit. And that makes it much harder for the theory side. That is, you have to come up with an explanation of why we would expect these just small things to just happen to resolve these tensions and anomalies. Okay, so let's talk about picking this up from yesterday, the leading tension. So I'd say brilliant agreement, 10%. That would have made me very happy 10 years ago, but of course now we're not satisfied with percent level precision. This pops out as currently a 4.4 sigma deviation, as we heard in the last day. And let me stress again that this is a tension to do with the anchors. So remember that the relative distances are set by all of the measurements at these intervening redshifts, linking the CMB through BAO to supernovae to the local anchors. And this discrepancy is really a discrepancy of the anchors. So you can take the Cepheid anchor here, go through the supernovae, and then predict what you would get for the sound horizon, or go backwards from the sound horizon to predict what you would get from the anchors. And nothing in between is going to be large enough to resolve this discrepancy. Now, you can reduce tension a little bit, and you can even get somewhat significant parameter deviations, but really you're not resolving this tension by anything in between unless you give up both something about the anchors and something about the links in the distance ladder. So let's talk about the CMB side. So the CMB anchor is the sound horizon. The distance sound travels by recombination, which means that given the exquisite calibration of the baryon density, both from BBN and from the relative heights of the peaks, the remaining parameter in lambda CDM is the matter density. Since we know what the radiation density is in standard lambda CDM, we know what the dark radiation is in neutrinos, and we measured the microwave background temperature. The only unknown is the cold dark matter density, and that appears in the microwave background mainly in the amplitude of the peaks. So remember that in the radiation-dominated universe, gravitational potentials will decay away due to the gene stability of the radiation, and that is going to drive the acoustic oscillation up. And very importantly, there are other effects that I'll talk about in the damping side that are consistency checks on the lambda CDM model, which the lambda CDM model has also passed, and is something that makes life difficult if you want to change the sound horizon. Okay, so let's talk about these little glitches and what they did historically to the Hubble constant, and also how they're relevant today in terms of the things that remain as residuals from the lambda CDM model at high L. So as pointed out in Addison et al., the difference between the W map H naught and the Planck H naught is a matter of the range you take in multiple space for extracting the cold dark matter density and therefore the Hubble constant through calibrating the sound horizon. And the very nice intermediate paper from Planck gave a very clear explanation and thorough treatment of this and pointed out that the explanation is sort of driven by these two areas of the data that have little deviations from the best fit lambda CDM model. That is this glitch, which we've known since WMAP, of this dip in power at L of 20 to 30. And then, as discovered by Planck, these oscillatory residuals that indicate smoother acoustic peaks. Okay, so how does this work? So if you just took the low L data, like in WMAP, you have this glitch here that says that if you wanted to interpret this in terms of parameters, you have this acoustic peaks being higher than you would suppose because of this low area here, which indicates more driving, less matter, higher H naught. But now with the Planck data, which go out higher, if you have this higher H naught and more driving, then not only do you get these higher peaks, but you get these oscillatory residuals that once you go beyond L of 1,000, you get this large penalty, which goes in, these are the acoustic peak scales that are marked out in these faint lines here, and you get things that are in-phase residuals to the acoustic peaks, and they go the opposite way if you try to raise H naught, so it's strongly rejected by the data. So there are two ways to think about this. You can think about this as omitting, trying to see what happens when you omit the L less than 30. That's the approach taken by the Planck team. And you get things that are consistent with the low H naught. If you drop this area, showing this, this compensation that I was describing. And alternately, what you could do is you could try to marginalize these features. So what we did in a paper from a few years ago is to take an inflationary spectrum that allowed for features here. And I don't think you should think of this as a detection of features, by the way, because it does improve the fit, something like 12, but you're putting in lots of parameters to do that. So I think you should think about this as another way of marginalizing the impact of the features, leaving you with the cosmology as determined by this area. And again, you return this low H naught value consistent with the full data set. Okay, so let's talk about that and the other end of the issue. So even the best fit lambda CDM, as we know, have these oscillatory residuals that indicate smoother peaks than the best fit lambda CDM. Driving of the acoustic oscillations drive the oscillations up. So there are sharper peaks, because there are other things that are smooth effects, like the Doppler effect and the ISW effect. And the residuals indicate that you should have less driving, a higher matter radiation ratio, and so a lower H naught. And that's how this fits together with driving H naught down in the Planck data set. All right, so this is the two effects in the temperature spectrum. The overall amplitude of the peaks as I change the cold dark matter ratio to radiation. And the other piece to that is these oscillatory residuals here on a compressed scale, log scale, that the peaks, you can see that they're in phase if you stare at this carefully. What I want to also say is that the polarization is a much sharper test of this. So we'll see that if you wanted to change the sound horizon by changing this driving physics, there are going to be signatures in the polarization that will be much cleaner and even distinguish between different ways of doing this if you could measure the EE power spectrum to equal precision that you've measured the TT power spectrum. So this is an opportunity to see both confirm the low H0 and test its origin, if there is a physics origin to this. Okay, and it's actually a little more extreme in the Planck data, because one of the 2 sigma fluctuations is a fluctuation around L of 200 of the TE power spectrum that I highlighted in those Planck legacy residual plot. And this is actually an important area. This is the important area for distinguishing driving effects. And it has an enhanced sensitivity because in the best fit lambda CDM model, it's a 2 sigma anomaly. And if you try to raise H0 by lowering omega CH squared, you go in the opposite direction. So polarization, just by chance, is actually more important than you would expect from, say, a Fisher matrix projection in the actual data. Okay, so let's go to thinking about models that might try to explain this. So if we needed to change the anchor of the sound horizon, we would want to change the amount of time sound propagates to change the sound horizon, because there's really very little room in changing the baryon to photon ratio. And you need a dark species that redshifts faster than matter, so you can change the sound horizon and therefore change all of these inferences. So we need to raise H0. That would lower the sound horizon and raise the inference of the CMB on H0 at fixed angular scale of the acoustic peaks. And then, because that has effects on the perturbations, if you add in extra radiation, you're making the driving effect more important. You have to compensate that by raising the cold dark matter density. And if you put that together in just the simplest ways of doing this, in terms of adding in extra relativistic degrees of freedom, this N effective parameter, you run into a problem with the damping scale. So we have 2 standard rulers in the microwave background, the acoustic scale for the sound horizon and the diffusion scale for the damping tail. The diffusion scale is this random walk of the photons in the photon baryon fluid, which means it's a harmonic mean between the horizon scale, the amount of time, and the Compton mean free path of the photons and the baryons. And that means it scales differently. It scales as the square root of the horizon, roughly the square root of the sound horizon, if you did something simple like raise the whole radiation energy density. And lambda CDM passes this test, so there's no evidence for a deviation in N effective, as we heard Monday. Whereas if you tried to solve the Hubble tension by adding in just extra radiation, you would not be able to satisfy this test. So that means that if you really wanted to do this, you have to go to more exotic dark components. So as pointed out in this paper from last fall, Poulin et al., one way to do this is to make the dark energy less important before equality. So you change the ability to change the horizon through radiation versus the damping scale by essentially timing this exactly right, by reconciling this ratio by having the right amount of dark exotica at the right time. And if this were the whole story, this would be unsatisfying, but maybe not horrible in the sense of the number of parameters that you're putting into this sort of model to explain the phenomenon. I would say that at the best, which I'll end up showing you that you can achieve this, but at best, you're putting in 1 parameter per phenomenon that you're trying to fix. The sound horizon and the damping scale are the 2 things that you're trying to fix here, and you need to have a timing and an amplitude parameter to get this ratio right. But also, as shown by Poulin et al., the perturbations are very important. So it's not just that, and you need more parameters generically. So the way they did it is they had a cosine potential of a scalar field raised to a power, and the perturbations in that kind of model are very important. Specifically, they had this thing where the position of where you start controls the effective sound speed. This is an effective fluid, and that we'll see drives the effects of on the microwave background. So what we did is open this up a little bit and think about a generic fluid component that's this dark exotica that is important at the matter radiation epoch. And think about this as a fluid with the ability to change the fluid in the background, the equation of state in the background, and the sound speed. So those are the crucial additional things that you need to think about. The basic mechanism works as stated, that you play with the amount of this dark component to fix the sound horizon. You raise the cold dark matter to try to fix the driving effects. So there's a compensation. We called this acoustic dark energy because we wanted to emphasize the acoustic oscillations in the dark energy that are important. They're subtly important in getting the phenomenology to match the data. And it's more general than the scalar field model. But that's the first level of compensation. But then when you're putting in the fluid, you have two extra parameters in all of these models, which is the equation of state of the fluid. So if you make the fluid less important at later times than equality, you're reducing the effect on driving. And if you change the sound speed of the effect, this is the first dark acoustic peak, if you like, and you change the position of that guy, you also change the efficiency of driving. So generically, you have these four parameters, and this model actually did have four parameters hidden in some of the initial conditions. You have the amplitude, the time scale, the sound speed, and the equation of state. And in this sort of oscillatory potential, the impact is that you'd have to be carefully tuned to start at the top of the potential in the anharmonic regime. There was also a paper by Agrawal that showed if you just have, Agrawal et al., that if you just have the power law portion of this potential, that you couldn't as efficiently change the Hubble constant. And the reason for that is that you need to have this, you have these two effects of the sound speed and equation of state, and you need to have a specific combination of those. But interestingly enough, that specific combination is something specific and generic. That is, you need the sound speed squared to be the equation of state after this starts to become important. And that corresponds to a scalar field which undergoes a transition between potential energy domination and kinetic energy domination. So unlike the original model where it oscillated in its potential, what you really want to satisfy this sort of condition is something that directly converts potential energy to kinetic energy and does not convert it back to match this. And that's fairly generic in the sense that that can be stated as the mechanism, and what you need there is to have the slope of the potential and the amplitude of the potential set to release you from Hubble drag at the right position. And those are the two parameters that control the amplitude and the timing of the transition. Okay, which leaves you with two parameters. If you're thinking about this as a scalar field, the slope and the amount. If you do that, you can, in fact, improve the fit to CMB, BAO, supernovae, and the Hubble constant by this fairly large factor of 12 to 14, 12 for the two parameters, 14 for three parameters, and in fact fits the CMB better, largely due to this anomalous region in TE, because once you have this ability to turn off this dark exotica between matter radiation equality and recombination, then you're left with the bare effect of raising the cold dark matter density, which we saw lowered this area, making you more consistent, raising the cold dark matter and making you more consistent with this glitchy area in TE. Okay, so the bottom line is that yes, indeed, if you throw in two parameters to fix up two things in the microwave background, you can improve the agreement with H0. And these extra parameters that you can throw in can get you further minor improvements. So here's the maximum likelihood at 72 or 72.5 for some of these cases. But you're left with the question that you've just converted this Hubble tension. So potential conversion was this is a pun, convert potential to kinetic energy. But what we've done is convert this H0 question to a why this, why then problem. So it's a coincidence. There's no explanation in these sorts of models for why we should pick matter radiation equality for when this should start, and why this specific amplitude and type of component. What I want to leave you with is that it's not the end, in the sense that if we're stuck with this being the cosmic variance limit and this being the resolution, that would be very unsatisfying. But even now, with the polarization data from Planck, if you add in the polarization, it starts to distinguish between these different mechanisms, in this case, the different parameters that you're putting into a model like this. And it's starting to separate the abilities to change the Hubble constant. So to say that more directly, if you look at the best fit model in this class of acoustic dark energy and look at the residuals that you predict from the best fit lambda CDM, but now in the EE polarization power spectrum, in this region, you expect these striking effects that would distinguish between models. In this region, you would have consistency checks on the damping tail and the change in the tilt. But this region distinguishes between the different mechanisms. And in these hundreds of multiples, each multiple is deviating by something like 0.3 versus cosmic variance. So the sum of all those multiples would lead to a strong test, both of this area that's crucial for the Hubble parameter in lambda CDM, and also is even now starting to distinguish between some of these alternatives. So I'll leave you with that. So I'll put on my lambda CDM hat again and say that Planck and other CMB experiments have established this model, this simple, elegant model, as the standard model of cosmology, unreasonably effective in the sense of 6 numbers predicting all of this phenomenology. Most things are predicted to sub% precision and mostly agreeing with everything, all of the other measurements, with these tensions being only at this less than 10% level, which is incredible. However, of course, imperfection is more interesting than perfection. If I'm putting on my other hat, it's always worth pursuing these. Although currently our models sound arbitrary, it's always useful to pursue these tensions and anomalies in the hopes of putting this all together in a coherent picture for how lambda CDM might break. And what you should look for there, illustrated by this Hubble constant example, is these are all designer models. So we're presented with a tension. We're trying to solve the tension. We throw in a parameter, hopefully just one parameter per effect. A lot of these alternatives, if you look carefully, are more than one parameter per effect you're trying to fix. So if we wanted to really start believing in these things instead of just working on these things, we would want to look for the predictive power of any of these explanations. And I've emphasized that this one in particular has predictions for the polarization that both can confirm the Hubble constant tension and also start to distinguish between these alternatives should it be physics. Thank you.
Okay, thanks very much, Wayne. Do we have any questions? Joe?
be interesting if there were another prediction other than polarization residuals.
It also
I wonder if
predicts...
you've thought of the following one, which is by adding significant extra dark photons at matter inequality, you're going to introduce potential fluctuations, and you're going to get inevitably some friction with the radiation, which will lead you to spectral distortions at some level. So that might be a way to...
Yeah, and these models have been conservative in trying to keep it in the dark sector and not alter the photons directly. And I should say one interesting aspect for model building is this coincidence that you're trying to do things at matter radiation equality, which has some hope of being just in the dark sector, some gravitational effect. Yes, so if you do something directly to the photon sector, then you will produce all of these other observables, which will be strong tests of any model like that. I should say that this class also predicts other things. So although currently it doesn't help, it has the same sigma 8 omega matter to the 1/2 as the lambda CDM model fit to TT alone. But there are deviations in the matter sector that will in the future also test these sorts of explanations, because you've done these compensations that currently are okay with the data, well, as okay as lambda CDM with the data. So it depends on how you view the sigma 8 tension. It does not help the sigma 8 tension.
But I think even with dark sector variations, adding so much dark sector fluid, you're going to have some gravitational coupling, which would surely lead to some implications for the black body spectrum at some level.
Don't quite see that. So I'm not doing anything to the photons. I'm not heating anything.
Gravitationally coupling, you're going to get variations and fluctuations, and they're going to be extra dissipation, I would think, at some level. Because it's like velocities.
Sure, yeah. Oh, I see what you're going after. Yeah, so we've changed the tilt of the power spectrum. So if you could measure the silk damping of the power spectrum, yes, yeah, but it's a subtle change, so you'd first have to detect things like that.
Okay, so one more quick question. No? Well, if not, let's thank Wayne again.
Can't quite see what I'm doing.
Hello.
Okay, well, next we have Alessandra Silvestri, who's going to be telling us about modified gravity.
Yeah. Thank you to the organizers for having me here, and thank you for asking me to talk about modified gravity right after nobody else than Wayne Hu reminded us how wonderful lambda CDM is. How do I stop it? Here. Yeah, it stopped.
You can
okay.
do it manually if you want.
Is this working? So now it won't go, right?
Yeah,
now I'm controlling. Okay, very good. So I'll pretend I didn't hear how beautiful lambda CDM is, and I'll give you an overview of possible alternatives, and mostly what we mean by modified theories of gravity, and how do we hope to test them using things such as large-scale structure and a suite of upcoming observations. So somebody once told me that it's not so surprising that we understand so well the early universe, but it's even more surprising that we don't understand much about the late universe. So we have this beautiful lambda CDM model. It is, though, a quite dark universe nowadays. And mostly, my research has to do with dark energy, one of the two dark components, the one that we associate with the accelerated expansion at late times. And basically by dark energy, I use the term dark energy or modified gravity, basically meaning more or less the same, and meaning an alternative to the cosmological constant to explain cosmic acceleration. So that pie chart that we get by fitting things such as cosmic microwave background and many other observables and establishing our lambda CDM model sits on the assumption that Einstein general relativity is the correct theory of gravity. Now, if we want to try to modify that, since that's the title of this talk, we should start asking ourselves, how special is general relativity? And if I want to go away from that, what can I do? So there's a couple of nice theorems and things such as Lovelock's theory of gravity that tell us what are the special features of general relativity. And the bottom line is that basically it's the unique theory that you can write out in 4 dimensions if you want to have a massless graviton that is mediating gravity. And it's a Lorentz invariant theory. So basically when you try to go beyond beyond general relativity, and hopefully trying to explain cosmic acceleration with something that is not a cosmological constant, you are left with some options. But the bottom line is that basically all of these options at the end of the day introduce a new degree of freedom in your theory. Whether you start from going to extra dimensions, whether you start giving mass to the graviton, whether you start introducing directly a scalar field, at the end of the day, especially for the range of scales and energy that we are probing with large-scale structure, for instance, you are introducing some new dynamical degrees of freedom, or if you want, you are changing what used to be constrained equations in general relativity. They're not anymore constrained equations in some cases, so you free up degrees of freedom. And in most of the cases, even if you started with massive gravity, these degrees of freedom show up in your observables as scalars. So there's a couple of things that you should be careful with when you modify gravity. And the 2 main that I want to mention are stability and consistency with local test of gravity. We do want to live in a stable universe, in a theory that makes sense and doesn't grow exponential instability as soon as you slightly perturb your solution. And I will go back to this argument, to this topic later in the talk. The other thing that you want to do is to be careful with local test of gravity. General relativity has been tested exquisitely well in local environments, in the solar system, around compact objects. And basically, all alternatives that you explore have somehow to go back to that and satisfy those, to go back to general relativity, basically in high-density regions and satisfy these constraints. So, okay, but let's try to think about going away from general relativity or going away from a constant dark energy, the cosmological constant. So there's many things, as I said, that you can do, but roughly we could think of them as going in the branch of directly introducing a new dynamical degree of freedom. So that's, if you want, you can call that branch dark energy, or rather modifying your laws of gravity on the large scales with the hope of achieving self-accelerating solutions when matter becomes negligible. There's a couple of alternatives in here, such as landscape and back reaction theories. But let me continue on the 2 main branches of modified gravity and dark energy. And if you want, you can think of this as the branch that the avenue that Einstein explored when taking us from Newtonian gravity to general relativity. And this one was instead the avenue that Leverrier explored when predicting new planets. So, okay, there you go. And then you can start having several models. We all know vanilla quintessence, minimally coupled quintessence, but you can start coupling your quintessence field minimally. On the other side, as I said, you can start thinking about giving mass to the graviton, breaking Lorentz invariance, and so on. And you keep going. And since cosmic acceleration has been discovered, we have kept going. And the result is quite a jungle of models. And what I want to stress are a couple of things. It's quite ineffective to approach cosmological observables with this jungle of models in mind. And also the distinction between the left and the right-hand side, it's not always so clear. A very nice example is f of r, which at the end of the day is a non-minimally coupled quintessence. So observations are coming to the rescue. We are living in a very promising era for observational cosmology, as we heard these days. And I always like to use this plot from Marco Raveri, Matteo Martinelli, Gongbo Zhao, and Wang. They have this nice cosmic fish code where they can make a lot of predictions and forecasts for what you will learn from upcoming surveys about many beyond lambda CDM models, where you can think of that also about as massive neutrinos. So there's a lot of information in this plot. It's basically looking at the relative information gain going from early times, COBE, all the way to present and to future, focusing on a couple of beyond lambda CDM models. This is the W0WA parametrization, for instance. This is a Lorentz breaking theory of gravity, and so on. And basically, all I want to stress out of this plot is the jump in information gain. You could think as now being a division between learning a lot and establishing with exquisite precision the parameters of lambda CDM, and now entering in an era when we can basically open our prism, and we can basically learn a lot also about all alternatives, whether we believe in those or not. But it's good to test them, also to increase our confidence in lambda CDM. So let me briefly review large-scale structure and how we want to use them to test gravity, the theories of gravity on the large scales. So for now, I'll focus on, for all the talk, I'll focus on linear perturbations. And so there's a big elephant in the room, which is the nonlinear regime, which I will not address. The other assumption that I'm going to make right now, and then I lift it, is scalar perturbations. So let us focus for a moment on linear scalar perturbations and in Newtonian gauge. So besides having the scale factor describing my expansion history, I have the two scalar potential describing perturbation to the metric. And you know, of course, expansion history, probe of expansion history will tell us about the scale factor and how it evolves in time. And then whether you're looking at things such as cosmic microwave background, weak lensing, the ISW effect, and so on, you are probing this combination, the sum of phi plus psi, that is the potential that enters in the geodesics of relativistic particles. And instead, if you look at things such as peculiar velocity and growth of structure, you are looking at geodesics of relativistic particles. So you're probing the potential psi. Now, just to remind you all about what lambda CDM entails for growth of structure, it is based, of course, as already said, on the laws of general relativity. And at late times, once neutrinos are negligible, we have mostly to focus on cold dark matter, which is pressureless. There's no shear. So at the end of the day, we have to focus on density perturbations to cold dark matter. Expansion is driven by a cosmological constant, so W is equal to -1. And if you do the exercise of studying how structure forms, you will find that since an isotropic stress is negligible, phi is equal to psi. And if you go to Fourier space, there is a very simple relation, algebraic relation, between your potential perturbation to the metric and the density contrast. Here I'm working in comoving with a comoving density contrast. So that's the Poisson equation, right? This is for all linear scales, super and subhorizon, as long as you are late enough that shear from neutrinos is negligible. That's what lambda CDM gives you. In other words, you can solve the equations for growth of structure and find that your growing mode is completely determined by the expansion history. So lambda CDM, if you want, gives you a growth of structure which is scale independent. You have the two potential phi and psi corresponding, being equal, and you have a consistency between expansion history and growth rate. We have learned, going through the exercise of studying growth of structure for some of the models in that huge jungle of models, that basically all these features break as soon as you go beyond lambda. So that has brought us to introduce some parameters, phenomenological functions, which are very effective in terms of capturing some features that could signal a beyond lambda in large-scale structure. So similarly to what you do with expansion history, and we introduce a dynamical, a time-dependent equation of state for dark energy, at the level of large-scale structure, you need two functions of time and scale, because now you're looking at perturbations. As long as you deal with linear scalar perturbation, those two functions are quite general enough to capture all possibilities. And they are designed in such a way that they are one in lambda CDM, and they will be something, typically a function of time and scale, as soon as you go away from lambda CDM. So if you haven't seen mu and sigma, you have for sure seen some of the other letters or functions used to indicate them, which is either G matter or G light, because you see they enter sort of in the geodesics for matter and light, and so they effectively rescale your Newton constant. Or gamma is an alternative letter, and eta, which is an anisotropic stress. So it's parameterizing the ratio between phi and psi. Now, we have learned something about these parameters. Of course, we have learned a lot since 1998 about W of A, but in recent years, different surveys, and in particular Planck already in 2015 and later in 2018, have started to put constraints on mu and sigma, or mu and eta here alternatively. So the anisotropic stress, whatever gives you a difference, introduces the difference between phi and psi. These are some examples of recent constraints on this function. More recently also from the dark energy survey, year one results. And you see again contours in W0 and WA, and some contours in, for the values of mu and sigma. So the rescale Newton constant for matter and rescale Newton constant for light today. This is their value today. So they marginalize over the time dependence of, and possibly scale dependence. But most of the in most of the cases, you tend to forget about the scale dependence and parameterize also the only the time dependence of this function. So I'm showing these more or less to make the following point. So I go back to the W0 WA contour from Planck. I use this one from 2015, which is very colorful. And so we have learned, we have some contours, some confidence in establishing possible values for these functions. And we will do even better with upcoming surveys, so even better, for instance, with Euclid. We'll shrink these contours down. Now, of course, I'm biased in putting this orange dot there. It could be anywhere in principle. But the whole thing to focus on is the relative size of the contours. So our confidence in establishing these numbers will significantly increase, though there is a big question remaining out there, which is what's the theory behind these numbers? So if we land on -1 and 0 for W0 WA, we know the theory. If we land in any other point of this plane, we might be left with the big question of what's behind this. So that's what we are trying to address right now. And I want to, in the remaining part of this talk, I want to try to address partially these two questions. That is, we will have wonderful numbers, but are we ready to extract the physics and the correct physics out of them? And the second question is, you see, I focus a lot on scalar perturbations. Those functions mu and sigma are born there. They're formulated for scalar perturbations. But there's a lot more out there. not only in polarization of cosmic microwave background, but now it's gravitational wave cosmology and astronomy and so on. So we are looking at tensor modes as well. And if I have a theory of gravity, the theory of gravity gives you dynamics for scalar, tensor, and etc. Everything has to be consistent. So is there a way in which we can factor in the complementary information that comes from those surveys? So again, back to this jungle, and let me show how we are trying to make progress in terms of theoretical modeling. So I will argue, for the purpose of this talk, and so if I have in mind large-scale structure and other cosmological probes, that most of the models that are in here could really well be represented by what are known as generalized Galileans, or in other words, Hordesky gravity, and which is an action here. You see a Lagrangian for the, in quote, most general scalar tensor theory, which second-order equations of motion. There's little exceptions, but basically, if you believe that your extra dynamical degree of freedom, whatever your modification is, will be at the end of the day a scalar, this is the, and you want to obey to have second-order equation of motion to avoid instabilities, this is the most general action that you can write. So we've made some progress in ordering that jungle. Still, we are facing several free functions of the scalar field and its kinetic term. So again, if you look at observables, it's not efficient to fit these two data. So I will argue that a good way forward is offered by the so-called effective field theory of dark energy, which was inspired by effective field theory of inflation and subsequently of quintessence, which is very closely related to spontaneous symmetry breaking, and so looking at your dynamical degree of freedom that is sourcing acceleration as spontaneously breaking time diffeomorphism. That's a very geometrical way of approaching dark energy, and I don't want to really get into the details of how this action is built. What I want to stress is that this is equivalent, as long as you look at linear perturbations, this is equivalent to the action that I had before. And I'm now parameterizing my ignorance about what my scalar degree of freedom could be doing in a handful, like 6 here, but they will reduce eventually, functions of time. So at least I've gone from function of scalar field and kinetic term to functions of time. Now, this is a quadratic action in perturbation, so you can study linear perturbation, but you can study scalars and tensors, because I'm just writing geometrical quantities in here. I haven't specialized yet to which perturbations to the metric I'm looking. And I skip this, the technical details of how this action is built. What I want to stress is that it gives you now a unified and physically informed framework. It has, with respect to mu and sigma, it has a very precise mapping to many of the models in that branch, in the jungle that I show. You don't need to resort to things such as quasi-static approximation, etc., to get the mapping of your model into this language. And you have, if you want, a very agnostic approach where you have unknown function, but you have also unified treatment for many models and many observables. So I'm going to show how there are several good things that you can do with this approach. And I'm going to focus on a few of them. I mentioned already stability and the fact that when you go beyond GR and you modify your GR, you have to be careful with the stability of your model. And a nice thing with respect to mu and sigma, a nice thing of this effective formulation through the action is that you can control the stability of your theory. You're starting from an action, so you can look at the stability of the perturbations around your background, and you do that by looking at signs of the kinetic term, the gradient terms, and things such as that. So let me give you an example, the very popular example of the phantom divide, and W, whether you can cross W equal -1 or not. With a single scalar field with a standard kinetic term, we know that you cannot go below the W equal -1 without developing phantom, without developing a ghost. So the argument is the following. If you start with a simple action with the scalar field and the kinetic term, and P here is a linear function of your kinetic term, so you have the standard thing. Then if you look at your perturbations in the scalar field, the corresponding action will be something like this. And now requiring no ghost implies that rho plus P for your scalar field has to be positive. And that's where you usually get the W has to be bigger than -1. Now, say that instead you have a different P here, that it can have some nonlinear term. So you are abandoning simple vanilla quintessence, you are making your kinetic term less trivial. Then there will be an extra operator in your action, and you see that you break this correspondence between the sign of the coefficient of the kinetic term being positive and W being positive. That's nice. You can go below, you can go in the so-called phantom region without being phantom, but you have to bear in mind that you have introduced an extra operator to be able to do that. And that extra operator will modify large-scale structure. So you have to be careful when exploring W0 and WA and using things that go beyond background probes, whether you are accounting for how you are going into the phantom regime. And so that's one way in which we want to use this effective approach, developing conditions of stability and projecting them into the regions, the so-called safe region, for instance, for W0, WA, and mu and sigma and so on. I'm going to skip this example that is based on Kidd's results because I'm going a bit slow, and go directly to theoretical priors. So using this effective field theory unified action, we want to explore the swath of models of gravity that, of course, correspond in this range of observables to introducing a scalar field with whatever coupling, well, whatever coupling is a bit exaggerated, but whatever kinetic term and so on, and study what are viable regions in terms of the phenomenology for large-scale structure. What is the phenomenology of large-scale structure that I can expect, say, if I start from Hordesky? But I want a stable Hordesky. And I'm going to call those theoretical priors. So this is an example of predictions that you can make purely theoretical. So these contours are theoretical. It's a mean and 1 and 2 sigma contours out of a theoretical distribution, sampling that action. So ideally, if I'm good at making a general sampling, I'm sampling in the whole theory space of here I'm restricting to things such as f of r, Jordan Brans-Dickey. Here I have full Hordesky. And here I have the Hordesky that doesn't change the speed of sound of gravity. So these are just, I mean, these plots are not going to tell you much, but are theoretical predictions for shapes that you expect for mu, sigma, and w. And our goal is to use them combined with data covariance matrices to reconstruct in a non-parametric way this function out of the data. Ideally, of course, it's a cumbersome task. Or you could also project these, if you really like things such as W0, WA, mu 0, sigma 0, and whatever, you can project these theoretical predictions into regions of your W0, WA. So let me show in a different way these theoretical priors. This is a bit cartoonish picture. So again, sampling through that action, the whole space of Hordesky. Here I'm looking at today, and at a very, I don't remember, I think it was quite a large scale, or no, probably, yeah, quite a large scale. What I do expect for sigma and mu, the center would be 0, 0, sigma minus 1, mu minus 1 is lambda CDM. In Hordesky model that somehow take into account local test of gravity, somehow that are stable, not somehow, but they are stable. Of course, it's a very tricky business, how you define stable, etc. And that also additionally, if I go to the red region, satisfy speed of sound of gravity being equal to 1 if we want to account for what gravitational waves and the electromagnetic counterpart have told us. So I have to finish. I want just to flash 2 more things. Gravitational waves, you know, I mean, there's been a big buzz about what we have learned about the speed of gravity once there was the counterpart detected. But there's also another nice feature that is not only theories of gravity not only potentially modify your speed of propagation, but also the friction term in here. And that will give you discrepancy in the luminosity distances inferred from gravitational waves and your electromagnetic counterpart. The thing that I want to stress is, yes, you can go and start picking which models survive CT square equal 1 if you strongly believe into that bound. But the main thing is I want to look at the implications of that, not much in terms of theories, but in terms of phenomenology of large-scale structure. And if you want to have CT square equal 1 within Hordesky, then you're bounded to do not see gravitational slip on large scales with Euclid. So Euclid is bounded to see mu equals sigma if we are within Hordesky. In the last minute or so, I want to touch upon another thing that I'm just learning. No expert. We have many experts in the audience, and we have learned a lot yesterday about strong lensing time delay, which is a very promising alternative probe of H0. And so we have, of course, asked ourselves, is there something complementary that we can learn out of there? We were very ambitious at the beginning. We thought about modified gravity, and then we scaled down to lambda CDM and WCDM and W0 WCDM, things such as that, like basically simple quintessence, because there's a lot that you have to worry about already in the standard case, but if you modify gravity, lens mass modeling, etc. So we are playing around with it. We are really beginners, but I think it's very interesting field. And we have been asking ourselves questions such as, so we are looking at the future, and we are doing some forecast with 10, 100, and 1,000, very optimistic scenario lenses with a good time delay measurements. And using the mock that we created in this way, we have been looking at how much our knowledge about parameters in lambda CDM will improve, but also things such as if I create a mock with a WCDM cosmology, and then I don't know, I mean, I assume my universe is lambda CDM, and I fit it with lambda CDM. What is the shift I will get in H0? Again, changing the number of lenses. And you do see that there can be a shift. So in here, the solid line is you fit your mock with the same cosmology with which you created, which was lambda CDM. Dash line, you fit it with lambda CDM. And you see the shift in H0. Final slide, then I stop. Then we go on, and since there is some shift, then could we build a sort of dark energy trigger by binning, if we are so lucky that we have many lenses, good lenses, on a good redshift range, here we are going from 0 to 1, could we bin them in, say, 3 redshift bins, and we create this catalog with WCDM, what we fit these bins with lambda CDM. We would find a discrepant value of H0 using the 3 different bins. So in principle, that could be also sort of trigger indicating to you that you are using the wrong cosmology to fit your data. And I really have very short conclusions, which is we are making progress. It's very difficult to think about beyond lambda CDM in a consistent way, in an unbiased way. And I think, though, the observational outlook is very promising, and I tend to push towards non-parametric reconstruction of our theory. And I stop here.
Thanks very much, Alessandro. Any questions?
Hi, thanks for the nice talk. So regarding the last part where you look at the bias when you fit with lambda CDM, where you mock up with WCDM, do you see a discrepancy in the fitting of like the distance? Like, is the mock data fitted less well with lambda CDM compared to the input?
So, in which sense? Sorry. Okay.
So when you mock data, are you mocking the distances?
Yeah. So you can look at maybe the error bars.
Right. This is the parameter constraints. But how about like the chi-squared?
Yeah, that I don't know. Yeah, that I don't know. So this is a sort of projection only on H0, and I can look at those error bars. That I don't know. Maybe the student that is doing it would know, but yeah.
Okay. Good question at the back.
Right, so still on the lenses, so what's the redshift distribution that you assume? Like, is it really good at constraining things like the acceleration, deceleration, transition redshift?
No, so here we have looked at lenses distributed uniformly in redshift from 0 to 1, and keeping the distance between the lens and the lensed quasar fixed to something like 1.2 in redshift. So we are at a sufficiently high, but not so high redshift. Yeah, you can still see, I mean, you are getting, especially if your number of lenses is good, you are starting to get quite sensitive to the expansion history. Your question is very relevant, and yeah, but yeah, presumably you will learn a lot, but yeah.
I have one final question from George.
Okay, so I mean, ultimately, what we would like to do is to have a, complete theory of quantum gravity. Okay, so my question is, in an effective field theory approach, do we have any idea of what might be realizable as a UV complete theory of gravity? What part of, the effective field theory space is likely to be allowed? Do we have any idea?
Yes and no. there is some corners of these theories that, yes, try to have a nice renormalization properties. There are things called weakly broken Galileans that you can reformulate in this effective field theory language, and so you can study their features at the level of large-scale structure in terms of this. I don't know of a way of, in general, imposing request of, on this action. But yeah, some corners of that do have those nice, promising properties. Promising.
Let's thank Alessandro again. Okay, well, our final talk before coffee is Savas Nasaris, who's going to tell us about the effective fluid approach in FFR and Hordensky theories.
Okay, thank you. So I'm going to talk about the effective fluid approach, which is a very nice approach that actually can describe any modified gravity model as an effective dark energy fluid. Now, this may sound like it's a bit trivial, but it's not, because it has the very nice advantage that if you want to calculate any interesting quantity like the matter power spectrum, the CMB power spectrum, you need to use a Boltzmann code. And in order to use a Boltzmann code, you have to take into account that all Boltzmann codes like Camp and class, they actually assume general relativity plus a dark energy fluid. And if you want to use your own modified gravity model like F of R or Hordensky, the equations are really, really complicated. And in order to modify the Boltzmann codes, you have to spend so much time and energy to do it. And there is also the potential for errors and bugs and so on. However, if you use effective fluid approaches I'm going to describe, then you can rewrite everything as GR and then effective dark energy fluid. Then you can just calculate the equation of state on all the other necessary variables. You just plug them in the Boltzmann code, and you are done. Now, this is a complementary approach to the EFT theory that Alessandro described. So I will say very few things about the EFT theory in a moment. Okay, so the reason that we need to do this, and the reason why this is interesting, is that we don't have only one modified gravity model. We actually have a plethora of modified gravity models. And the reason for this is that if you have some data, some cosmological data or whatever, and you go to a theorist like me or other people, I see many familiar theorists in the group, and you tell them, okay, I have this data and I have a problem, give me a model. We're not going to give you just one model, we're going to give you a bazillion of models. So this situation has created a whole zoo of dark energy and modified gravity models, which is The problem with this is that all of these models, they have their own parameters, their own structure, their own equations, so there is really no unified way to describe all of them. Okay, so there are some classes of models like Hordensky that contain various subclasses like f of r and so on, but in general, as I will describe in a moment, this plethora of models is so different and they have different characteristics, so it's very difficult to take them into account, especially at the technical level in the Boltzmann code. Okay, so I'm going briefly to describe the situation about the dark energy model zoo. I will say a few things about f of r models and Hordensky theories, and then I will describe the effective fluid approach, the advantages and the disadvantages of the method. Okay, so almost 90 years ago, we realized by Hubble's observations of distant galaxies that the universe is actually expanding, and 20 years ago we realized that the universe is also accelerating, which means that all known forms of matter, they cannot explain the accelerated expansion of the universe, because for baryons and, I don't know, neutrinos and photons and so on, gravity is actually attractive, which means that they would make the universe actually decelerate and collapse on itself. So we need an extra component that will drive the accelerated expansion of the universe. And as I said, since we theorists have a large imagination, we can think about crazy models and so on, then we have a whole zoo of dark energy modified gravity models. So I'm saying this is a zoo because you have all sorts of various beasts hiding in there, and it's nice to put them, to categorize them in some form. So for example, in most traditional zoos, at the center you have your favorite cute animal that you want to play with, like dolphins or seals or whatever. So we are going to put GR at the center. And around GR, we will have various extensions like f of r theories, but also theories with Riemann and Ricci tensor contractions with Gauss-Bonnet terms and crazy stuff like that. But you also have even crazier alternatives like theories with two metrics, theories that are non-local, theories where the vacuum is running, or theories with torsion or weird modifications of Mond, and also one of my favorites, so massive gravity. And by the way, the animals that I chose in this picture, most of them are by accident, but for massive gravity on purpose, I chose the elephant because the graviton is actually heavy. So, and by Otto also you have other alternatives. So for example, these are more traditional stuff where you have scalar fields either non-minimally coupled or minimally coupled, but also Chapel-Jean gases and Galileons, and of course the Hordensky theory, which encompasses some of these models. And there are also some other cases that come from string theory, that are inspired by string theory and models with extra dimensions, like Randall-Sundrum, DGP, Kaluza-Klein, but also theories that come from the UV completion of gravity, like Horava-Lifshitz and conformal gravity. So as you can see, there is a very large variety of models, each with its own characteristics, like extra dimensions or scalar fields or weird modifications and so on. And there's really no standardized, unified way to describe all of them and put them in the Boltzmann code. Because at the end, what we're going to do is take these models, put them in the Boltzmann code, and see what happens. Now, in the previous lectures, we saw that actually lambda CDM can describe very well the cosmological data, but in the end, we also need to study these models and see if there is some deviation from lambda CDM. Okay. So, as I said, there is no clear unified approach. This was a bit of an exaggeration. There are actually two approaches. The first one is the EFT approach discussed by Alessandra. So she described it very well, so I'm not going to say very much about that. So this, the EFT approach was pioneered in cosmology, was pioneered by Alessandra and collaborators. And the idea actually comes from particle physics, where people, they want to test for deviations from the standard model and test for BSM physics, beyond the standard model physics. So they consider all the various operators that you can come up with up to a specific order. And then you try to fit and constrain the couplings. Now, in particle physics, they have something like 30 operators last time I checked. But in cosmology, the situation is a bit better. So in the end, we need something like 6 parameters, which, as Alessandra said, you can map to various models. And also in the end, you can put this in a Boltzmann code. They have a very nice Boltzmann code called the EFT camp. And you can have a look if you want. Now, there is another complementary approach, which is the effective fluid approach, which, as I said, you can map any modified gravity model to an effective dark energy fluid. And this is very trivial to do it at background level, but also at the linear order. So what you do is you write down your equations of motion for your modified gravity model, which in principle can be horrible, nightmarish, I mean, very complicated expressions. And then what you do is you just extract gravity, you extract, the Einstein tensor, so general relativity, and you see whatever other matter component you have, like neutrinos, radiation, whatever. So whatever remains, you call it an effective dark energy fluid, And on the background level, you can just extract the pressure and the density of this stuff. I will show you in a moment how to do that. And at linear order, the only thing that you need to describe the perturbations at linear order is actually 2 first-order equations for the evolution of the density contrast of the dark energy and for the velocity of the fluid, because a fluid in general will also have some velocity perturbations. And in order to solve these equations, you just need the sound speed, the equation of state, the isotropic stress. So if from this approach you can extract these parameters like the sound speed, the equation of state, the isotropic stress, then practically you are done. So in a nutshell, just to summarize again, what you want to do is rewrite everything like GR and an effective dark energy fluid. Then you will extract your quantities like the equation of state, you plug them in your Boltzmann code, and you're done. So this is very powerful because you can map all the various models to practically 3-4 parameters, because at the linear level, we don't have enough freedom. I mean, you only have freedom to describe the sound speed, the equation of state, and then isotropic stress, and practically that's it. Okay, so this is the only freedom you have practically. Okay. So before I discuss exactly how you do that, I want to say a few things about FOR models and Hordenski theories. So FOR models are the easiest modifications you can do to general relativity. So you start with your Einstein-Hilbert action, which is described just by the Ricci scalar, and then you promote this to a function of the Ricci scalar. So the idea is quite simple. You change this from the Ricci scalar to a function of the Ricci scalar. This implies that what you do is you introduce a scalar degree of freedom. Okay, so at this level, it's just a scalar degree of freedom, but it has the advantage that it has been very well studied. In the past, it was actually used as an inflationary model by Starobinsky sometime in the 70s, 60s or something. So the model that he proposed, it was just the Ricci scalar plus r squared. And as I said, the dynamics are very well understood, but it has rich phenomenology. So for example, in these models, Newton's constant is not really constant anymore, but it depends on space and time. And it's also high energy physics inspired, as I will discuss in a moment. Now, a funny thing about these theories is that the cosmological constant model is actually a special case of the FOR theories, because if you just do a Taylor expansion around some background, then you can say, okay, my constant term is just the cosmological constant, and then the derivative term is just a rescaling of the bare Newton's constant. So practically, this tells us that the cosmological constant model is not something really truly special. It's just a specific case of a more general theory that probably lives in higher energies. Okay, so this is interesting because if you start thinking about gravity at higher energies, and you actually try to renormalize general relativity. So general relativity is not in general renormalizable, but you can renormalize it to first loop order. So if you try to do that, you can see the details in the book of Birrell and Davis. Then you start picking up some quantum corrections. And these quantum corrections, they include terms like Riemann and Ricci tensor contractions. They include terms like r squared, which is quite funny because this is exactly similar to Starobinsky's model, so r plus r squared. And then you also get some stuff like box r, so the box is the D'Alembertian operator. Now, the box r term on its own is actually 0 because this is a total derivative, and if you don't have any surfaces and so on, then this will go to 0, it will vanish. But it's actually funny because it reminds us of non-local theories. So non-local theories, if you are familiar with them, you can write them as an infinite sum of box terms. So the fact that even we get just the zero-order term of these theories could imply something. I'm not a very big fan of these theories, but some people are. And the interesting thing you can do is then you can start thinking, depending on how crazy or how high you are, you can start thinking about various pure modified gravity theories that include all sorts of Ricci scalar, Riemann and Ricci tensor contractions, box terms, and Gauss-Bonnet terms. So the possibilities are really infinite. So this is a good thing because you have lots of freedom. You can play with your theories and you can have fun. But it's also bad because it's really, really difficult to actually put constraints on these theories, because if you have some weird theory like this, you need to put it in the Boltzmann code, you have to make modifications. If you have another theory which is quite different, you have to do the same thing again, which is really time consuming. Okay. Of course, in practice, most of these theories, they have problems with Gauss, Strogatsky instabilities and stuff like that, so most of them are actually ruled out already. But in principle, you can find some theories that are viable. Okay. So, one important thing is that, as I said, for the effective fluid approach, you have to take the equations of motion, extract general relativity, and whatever remains, you just shove it on the other side, and you call it a dark energy fluid. So for FOR theories, the equations of motion look like this. They're a bit horrible, so they have derivatives of the Lagrangian with respect to the Ricci scalar, or covariant derivatives and box terms, so they're really, really horrible. But the nice thing about them is that they satisfy conservation equations. So they satisfy a generalized Bianchi identity. So by doing some algebra using the diffeomorphism invariance of the theory, you can show that actually this term is conserved. And this is interesting because if you want to express this as an effective energy momentum tensor, your energy momentum tensor has to be conserved. Otherwise, it's useless. But the nice thing is that this thing, and by S, I'm calling all of the left-hand side, this is conserved. Okay. Now, another thing is that if you play with the Robertson-Water metric, you can actually write down your modified Friedmann equations, and then if you choose your Lagrangian property, then this can drive acceleration, the accelerated expansion of the universe. And some people have already created models that do that. For example, there's the famous Wien-Sawicki model, but there is also another model by Starobinsky. So Starobinsky is very prolific at creating modified gravity models, so she produces them at a nice rate. And they have this following property. So the Wien-Sawicki model, initially it was written in this form with some parameters like M, C1, and C2, but if you do some clever algebra, then you can reduce it in the form which is reminiscent of R minus 2 lambda, the cosmological constant, divided by some factors of the Ricci scalar and some parameter B. And when this parameter B goes to 0, then this is just lambda CDM, and then when parameter B goes to infinity, then you get a purely matter-dominated GR model. Okay. So this is interesting because it explains very well why this model passes all solar system tests, because practically it's a small perturbation around lambda CDM, and that's why it's very successful. And the same thing applies also to this specific Starobinsky model. Okay. So let me say a few things about Hordensky models. So Hordensky models, they include the scalar field along with its kinetic term, and they have the following 4 Lagrangians with some 4 unknown functions that depend on the scalar field and the kinetic term. Now, the nice thing about these theories is that they have second-order equations of motion by construction. So Hordensky included this, let's call them counter terms in the language of particle physics. So he included these extra terms that cancel the higher order derivatives, and this makes the equations of motion being second order. This is important because if your theory has more than second order equations of motion, then it will suffer from the Ostrogradsky instability, and then your theory is dead, practically. So these theories, they have second order equations of motion, so they don't have problems like this. As I will show in a moment, they also contain lots of other models like F of R or kinetic gravity braiding models and Galileans and so on. However, they also have a couple of problems. So first of all, these terms practically have been excluded by the gravitational wave observations of the speed of the gravitational waves. And some of these terms, especially these guys, they're not really motivated by high energy physics. So some of the models included in the Hordensky theory, like F of R and Brans-Dicke and Galileans and so on, you can say, okay, they are motivated by high energy physics, especially the F of R. But there are also some other terms like this one, which has no motivation at all. So in my opinion, this is a problem for the theory. Okay, so as I said, these theories include all sorts of subcases. So if you choose your functions, G2, G3, G4, and G5 properly, if you are smart enough, then you can include like theories F of R, Brans-Dicke, and so on. So this already includes lots of cases, and if you are able to put your Hordensky or your effective fluid of the Hordensky in some code, then this already covers lots of cases. Okay. Now, one last thing I would like to say about the F of R theories and the Hordensky theories is that we know, as we saw also in the previous lectures, that the background is actually very well described by lambda CDM. Okay? So this seems to be the case as we see from CMB measurements and so on, which means that if we want to detect deviations from lambda CDM, it would make sense to actually fix the background to lambda CDM and then try to see if something happens at the perturbations level. One way to do it with these theories and make sure that our background is exactly lambda CDM is to use the so-called designer models. So there is already an F of R designer model which does the following thing. So your background is exactly lambda CDM, but it's allowed to have perturbations. And the way you do that is you start with your F of R equations of motion or with the modified Friedmann equations. You demand that the background is exactly lambda CDM, and then you try to reconstruct what is your Lagrangian. Okay. So if you do that for F of R, many people, including myself, Alessandra, and others, have rediscovered again and again what is the specific F of R designer model. So in this case, the Lagrangian is given by this horrible form. So it's R minus 2 lambda and the hypergeometric function with some weird coefficients. But you don't really have to worry about that because you can also find some power law expansions valid at late times. So at early times, everything looks like lambda CDM, but at late times, it looks like a power law, so scale factor to some power. So you don't really have to worry about that. Also recently, with my PhD student Ruben and collaborator Vilmar Cardona, we also managed to find a designer model for Hordensky theories, which is of the KGB type, of the kinetic gravity braiding model. So again, you start with the Friedmann equations for these models. You demand that your background is exactly lambda CDM, and you try to find what is the Lagrangian. So in this case, you can find the Lagrangian, like the function G3 and G2. Also, some people call G2, they call it K. So then you manage to find the Lagrangian in terms of the kinetic term. And then the advantage of this is that you have exactly the background that is lambda CDM, and then you can start playing around with the coefficients and see what's happening with the perturbations. Okay. Now, let's talk about the effective fluid approach. So as I said, the effective fluid approach is quite simple. So what you do is you write down your equations of motion. So you write down your equations of motion for the theory that you have, and then you just extract the general relativity. So for example, if you do this for the f of r theories, as I said, the equations of motion are given by this horrible expression, but I can just reshuffle a bit of the terms, take out the Einstein tensor, send everything on the right-hand side, so I can write it as the Einstein tensor, so GR, the usual matter that we have, and an effective energy momentum tensor, which you can write in this form. The nice thing about this is, as I said, that it's already conserved, so we don't have any problems with that. And it also makes life easier because if you have your Boltzmann code, you can just extract the various components of the energy momentum tensor. So for example, the 0,0 part gives you the density, the background density and the density perturbation. So you can just write 2 liners of code in Mathematica and you just extract what is your density and the background density of the perturbations. You can do the same for the velocity and the anisotropic stress. Okay. So specifically, if you do this exercise, you write down your effective energy momentum tensor, you extract the background density and the pressure, you see that it's given by these expressions, and then you can just rewrite your Friedmann equations in the more traditional form with some dark energy density and pressure, and then you can also calculate the equation of state, which is the ratio of these two, and then you see, for example, for the Quinn-Savitsky model in terms of this parameter B, that your equation of state is a small perturbation around -1. Now this is interesting because if I just give you this horrible equations of motion, you don't have any intuition. You say, okay, whatever, it's some weird funny equations, okay, whatever, I don't understand them. But if I tell you that for this model, the equation of state behaves like this, then you already have an intuition, so you can understand how this model will behave. Okay, so in this case, at least at the background level, this helps a lot. And you can also do the same thing in the perturbations level, so you just decompose your energy momentum tensor, you pick up the perturbations for the density, the pressure, and the anisotropic stress. You plug them in the equations for the perturbations that I discussed, and then you're practically done. Okay, so that's it. Now, of course, one important thing you need to study is the stability of the theory, and the one way to do this is you can eliminate the velocity from this system of equations, and then you have a second-order differential equation. So this is going to be some damping term, the driving term. And then you will have on the right-hand side a force, which contains the potentials, the sound speed, and the anisotropic stress. And then by doing some simple analysis, you can understand that this term has to be positive, otherwise your system will crash. Okay. Now the thing is, in most realistic models, this term 1 plus w times psi will actually be close to 0 because w is close to -1 and psi is suppressed by orders of k squared. So the only thing we are interested in is that this combination of the sound speed minus the anisotropic stress is positive. So we can define the so-called effective sound speed, and then we can demand that this thing is positive. And one thing we can do actually for the f of r model is if we calculate all of these quantities, we just extract them from the energy momentum tensor, then we can actually calculate the effective sound speed. And even though our regular sound speed is negative, actually the sound speed for this model is something like -2/3. And you might say, hey, my sound speed is negative, so this model is crap. But it's not, because your effective sound speed, which also includes anisotropic stress, is actually positive at early times, and then it goes to 0 at late times, which means that I expect my effective dark energy perturbations to grow and then just reach a plateau and stop there. And this is actually exactly what happens. So I'm showing here the evolution of the perturbations. So the orange line is the dark energy perturbations, the density perturbations, and this is the velocity perturbations. And you see they start growing, they reach a plateau, and then they just stop there or even go down, which is in agreement with what we expect. Okay. So the question is, now we have all the tools, so how do we put all of this stuff in the Boltzmann code? So as I said, the only thing that you need is to have these quantities. So for example, for the f of r model, you just need to calculate these functions, which is like 4 lines of code. Okay, so you calculate your pressure perturbation, the velocity perturbation, then isotropic stress, just 4 lines of code. And then you just put them in the Boltzmann code. Now, in our case, we have done this. So we modified the class code because it already includes a dark energy model with sound speed and so on. And then we compared with various other codes like mgcamp and frcamp. So in this plot, you can see the TT part of the CLs, of the CMB power spectrum versus the multiples. Now, the main effect of these modified gravity models is going to be at low multiples, so at the ISW level. And everything else is more or less the same. So for comparison, I'm showing in the blue line lambda CDM. Then the green line is our code, EF class, which, by the way, even though we were told not to do any sales pitch, I'm a bit shameless, so you can find the code in my website and also on GitHub. And then we also compared with other codes like mgcamp. So for example, one problem with mgcamp, at least the version that we used at the moment, was that the background was not properly coded, so mgcamp used lambda CDM at the time. But for the Huyn-Savitsky model, this is not correct, because the Huyn-Savitsky model interpolates close, it oscillates close to lambda CDM, but it's not exactly lambda CDM. And this amplifies the deviation at the ISW. So you see it has a bit of a difference. And we checked that our code EF class gives the correct ISW by doing a brute force ISW calculation. So this is the correct result. However, if you use the designer model, because the designer model has exactly a lambda CDM background, then we also compared with EFT camp and another code called class EOS, and then all of them give more or less the same result. So they were in good agreement. But the most surprising thing for me was that we also compared, and this is my final slide practically, we also compared with the Hordensky models. So for the Hordensky models, there is a code called high class, which was developed by Miguel Zumalacari when he was a PhD student at the AFT in Madrid. And this code actually solves the whole complicated mess of perturbation equations in Hordensky. So you see there's something like 20, 30 equations which are really coupled with each other, and you have to be careful about initial conditions and being able to follow the attractor. So it's a whole complicated mess. So he managed to solve this thing, and he modified class to include these models. So he calls his code high class. But with our effective fluid approach, at least for the designer model, the only thing we need to do is just calculate the velocity of the perturbations of dark energy, because the designer model doesn't have any pressure perturbations and doesn't have any anisotropic stress, only the designer model. And then with just one line of code, we were able to get almost 0.1% accuracy, which is like amazing with one line of code. So as you can see, the effective fluid approach, it might sound sort of trivial, but it's not, it's quite powerful. So what it can do is you can have a unified approach and describe all of modified gravity models in terms of 3-4 parameters, because at the linear level, this is the only freedom that you have. So even though your theory might have, I don't know, a bazillion of parameters, in the end, at the linear level, this is the only freedom that you have. And if you want to calculate something interesting using a Boltzmann code, you can use the effective fluid approach to map all your models and then just make simple modifications to the Boltzmann codes, and you're done. Okay, so I'm going to skip this stuff and leave you with the conclusions. Okay, thank you.
Yeah. Thank you, Soas. Any questions? Dan? Yeah.
Yeah.
So,
can you?
is the thanks for a nice talk, by the way.
Yeah.
Is the effective fluid code significantly faster than the high class code? And kind of as a follow-on, looked like there were percent level differences. Are those limited to low L, such that you don't need to worry about this for parameter estimation because you're just in the cosmic variance limited regime?
Okay, so the effective fluid code is way faster than high class, because high class has to solve all these complicated equations, so it's a bit slower. Now, about the percent differences, actually, the blue line that you see there is actually lambda CDM, and the high class code is actually overlapping with our code. So it's the orange and green line that actually overlap there. You don't even see them. So the blue line that you see is lambda CDM. And here I'm plotting the percent difference, and you can see it's like multiplied by 100. So this is 0.1%. So between the two codes, between EF class and high class. So the agreement is really, really good. Now, 0.1% in the future might not be good enough, but for the time being, I think it is.
So let's talk a little bit about the challenges.
Yep.
There are a lot of interest for things like bispectra and so on, which all require second order. So, well, you say this is difficult. I mean, is this doable? Are you making progress? What are the main difficulties? I mean, you know.
Okay.
Considering that this is solved at linear order.
Yeah, so as I said, exactly, everything is at the linear order. So for the time being, we haven't thought about going to second order because it's a bit complicated. But in principle, one should be able to write an effective fluid approach also to the second order and try to map all the models to that case. But for the time being, as far as I know, okay, we haven't done it, and I don't know if anyone else has done it. But that would be a challenge for the future.
How long do I have to wait before I invite you again to talk about it?
Okay, I don't know, next year? now that you gave me a challenge, Okay.
Okay, well, we're going to break for coffee now. We reconvene at 11 o'clock. And can I just ask all the speakers in the second session, particularly those giving the short poster talks, can you just come and check that everything's working correctly? But, let's thank Savas again.
I'll check it's working. So
You made the title longer.
Can I check if my computer
hey,
will work here?
yeah, sure. So which is the connector?
HDMI. This one is
this
fine.
One, this
yeah.
one is fine, right? You can
I
just
guess
check
that's
it.
not HDMI. That's done. But yeah, that's the right one.
Yes, I know. Hey.
Bonjour. Hi.
You well?
Yes, good.
Looking forward to your talk.
Sorry?
I'm looking
yes.
forward to your talk.
Yes, thank you very much.
Okay, well, welcome back, everyone. So our first talk this session is from Cyril Pitrou. He's going to tell us about the status of Big Bang nucleosynthesis.
So, can you hear me? Yes. Yes. Can you hear me? So thank you for the invitation. So I'm always a bit uncomfortable when I'm talking about BBN in the cosmology conference because BBN is really part of cosmology in the sense that it's really central for the cosmological model, but it's always a side topic because it's only a small measurement of a few abundances in the sky, and it's not a big collaboration, but it's very central. That's why I had decided to work on that 2 years ago with some collaborators in IAP, and I'm going to review the stages of the standard Big Bang nucleosynthesis. So what's the main difference between nuclear physics and between recombination and Big Bang nucleosynthesis? It's a matter of scales. Recombinations, it's when you have a proton plus an electron which is recombining into hydrogen, and this gives a photon of the order of energy of the order of a few electron volts. For nuclear reactions, the typical reaction, the central reaction in the early universe is a proton plus a neutron gives deuterium. This is the first reaction which creates nuclei, and then from this reaction we're going to create other nuclei. And the main difference is that for recombination, since we have electron volts, it corresponds to times which are about, let's say, to a scale factor which is 1,000 times smaller, whereas this is much earlier in time, and it is right after Big Bang, you could say, just because the typical energy scales which prevent the synthesis of nuclei is of the order of the mega-electronvolt. So when you have energy which are larger than the electron volt, then you cannot have recombination, and the universe is not transparent. When you have photons which have energy which is more than a few mega-electron volt, then you cannot form nuclei. So you cannot have nucleosynthesis. So this is very well summarized in this plot. Here you have the scale factor, which is 1 today. It's 10 to the minus 3 around the recombination. That's where you have all the CMB physics. And just the fact that you need to go at scales which are of the order of the mega-electron volts reduces the scale factor by 10 to the minus, another 10 to the minus 6. So now the scale factor for BBN is around 10 to the minus 9. And in terms of year, you see it's just a fraction of year. And in fact, it's just a few hundred seconds. So it's very, this scale is going from electron volts to mega-electron volts, makes it going from 300,000 years to the very early universe. Now, the other thing which is important for BBN is that since it's so deep in the matter-dominated era, the matter, at least the gravitational, at least matter does not play a role gravitationally. So we can really say that the expansion rate is completely controlled by the radiation content of our universe, so which is made of photons, but also neutrinos, and if we are looking for exotic physics, possibly other species. And so this radiation, which is scaling 1 over a to the 4, when you plug that into the Friedmann equation, then what you find directly from the fact that radiation is scaling like t to the 4 and 1 over the scale factor to the 4, directly you find a very crucial and important scaling in the early universe for BBN is that the temperature square is scaling like 1 over the time. And this is very important. I'm going to show you in a few plots. So the main things about BBN is that we can form nuclei precisely from the very fact that in the very early universe we have neutrons. And that's the main difference with stars. In stars we don't have neutrons, so we have to wait for weak interactions to transform some protons into neutrons, and it takes a lot of time. That's why stars live very long. Whereas in the early universe, we can have a statistical equilibrium between neutrons and protons due to these weak interactions. Neutron plus neutrino gives proton plus electron, and all the other types of reactions. And this is only given by the Boltzmann factor, the statistical equilibrium. So it's the number density, so N here stands for number density of either neutrons or protons, is given by exponential minus the energy divided by kBT. Since everything happens around the MEV, it means that the typical energies of protons and neutrons is completely dominated by their rest mass energy. So the number density of protons is exponential minus their mass divided by kBT, and the same thing for neutrons. And from the very fact that neutrons have 1.3 mega-electron volt more in mass, means that there is a suppression of the number density by this exponential minus 1.3 MeV divided by kBT. This is in MeV. So which means that much before the time where the typical temperature of the order of the MeV, then we have 50% of neutrons, 50% of protons, and for temperature which are much less than 1 MeV, and this is very crucial, then we will have much less neutrons. And so since we lose neutrons, then we cannot form nuclei as efficiently as if we have a lot of neutrons. So this is typically what's happening for neutrons. So you have to look at this continuous line here. And the dashed line is what you would obtain from the statistical equilibrium. This is time, 1 second, 10 seconds, 100 seconds. So I told you this is very early in the universe. Here you have 1 MeV, and you have 10 MeV. So you see there's a scaling that when you reduce the temperature by a factor 10, you increase the time by a factor 100. And here, around that time, you don't have enough weak interactions to enforce statistical equilibrium. If weak interactions were not that weak, then we will have statistical equilibrium, and much below 1 MeV, so around here, then we will have a strong suppression, it's just a statistical suppression, and then we would have no neutrons left, or just traces, and so we're not able to produce helium-4 efficiently. But since weak interactions are rather weak, at some point they are not efficient, so there is a freeze-out of these weak interactions, and so the neutrons are frozen, and we should reach a plateau. But we do not reach exactly a plateau here. We have a neutron beta decay. And so that's the first part in BBN where the neutron lifetime plays a role, because here, instead of having a plateau, we are still losing neutrons between there and there. Around 100 seconds, or actually 200 seconds, then we are much below the mega-electron volt, so we can start to form deuterium. We can start to have these reactions going from the left to the right, and not to have enough of the reactions going from the right to the left, because we don't have enough energetic photons. And so we form deuterium. And so you see that what controls exactly the amount of nuclei which are formed are the time at which there is this freeze-out. If weak interactions are more efficient in the early universe, then we will freeze out later with less neutrons, and so then we will form less nuclei. So this is the same plot, but with a linear scale in time. So here you see you have the statistical equilibrium which is enforced. this is the neutron abundance. It would go like that if weak interaction were not that weak. But then we have this freeze out, and instead of reaching a plateau here, we still have beta decay. And you see between the freeze out here and here, we have 200 seconds. Since the tau in the beta decay, you know, decay like exponential minus t divided by tau is about 800 seconds, you see that in 200 seconds, we are losing a sizable amount of neutrons just because of neutron beta decay. So any change in this neutron beta decay will change the amount of neutrons which are left here when we can start to form nuclei. And here I've put half of the helium-4 because nearly everything eventually goes into helium-4. So here, nuclear reaction starts to use the neutrons. Neutrons are all used, and they're all used. Essentially, all of the neutrons are going into helium-4. Now, another thing which makes BBN so powerful for cosmology is this difference between here, freeze out, and here when we start BBN. Because freeze out depends on the temperature and on the efficiency of the weak interactions. And here it depends on typically on the binding energy of deuterium. The temperature at which we can start to form deuterium depends on its 2.2 mega electron volt of binding energy. And so the time between here and here depends on the cooling speed of our universe. If I add an extra species, which is just a spectator species, but which is relativistic, so which acts like an extra radiation, then I will have a larger Hubble factor, so a faster cooling speed. So I will spend less time between this temperature and this temperature. If I spend less time, I have less neutron beta decay, so I have more neutrons here when I start BBN, and so I produce more helium-4. So that's essentially why BBN is used to constrain the number of relativistic degrees of freedom. It's between the fact that it changes the time here, and so it changes the final abundance of helium-4. So here, weak interactions, they control the abundance between protons and neutrons. So protons it's hydrogen. And then we have all other types of nuclear reactions, so the one which creates deuterium, the one I mentioned. And then you have a whole network of nuclear reactions which end up in forming essentially just helium-4. But we will have remnants of helium-3, deuterium, lithium-7, beryllium-7, and so on. And then you can even put all the reactions that you know and which have been tested in labs and predicts what are the abundances the abundances of the various light elements due to the Big Bang. So this is typically the plot that you get. Here, this is the number of protons, which is staying around 75%. This number of neutrons, which are used here by the nucleosynthesis. You produce deuterium, which is then used. Deuterium is used here to produce helium-4. In the end, you end up having 25% in mass of helium-4, traces of deuterium, helium-3, traces of beryllium-7, lithium-7, and so on. So this is typically the kind of plot you produce with BBN when you want to do cosmology, or at least when you want to get some constraint. But this is an historical plot. And this has changed a lot for two reasons. The very first reason is that we used to plot BBN predictions in terms of the baryons abundance, because essentially when you look at the physics during BBN, it only depends on the ratio between the baryons number density and the photons number density. And so before the CMB era, we didn't know exactly what it was, so we used to do these plots confronting the measurement in helium-4 to the predictions, which is in blue. The same thing for deuterium. Measurement is in green, and the theoretical predictions is in blue in terms of baryon abundance. And then you have helium-3, which is not very well measured, and you have these lithium-7 problems. But what has changed since WMAP is that we had a value for the baryon abundance just coming from the baryon acoustic oscillations, so from the peaks of the CMB. We had a first guess, a very good guess of the baryon abundance in WMAP. And then starting from Planck, now we have not just a guess, we have actually a very good value for this baryon abundance. So this kind of plot is completely outdated. Now, BBN has to be there. The baryon abundance is given by CMB. And if the predictions for this value of the baryon abundance matches the prediction in blue, if the observation matches the prediction in blue at this baryon abundance, then BBN works fine. If it doesn't work, then it's a mess. So the fact that it works fine for deuterium, on which we have very precise measurement, 1.2%, and very well for helium-4, on which we also have very good estimation, which is with error bars which are of the order of 1.6%, means that the cosmological, and that's what I like in BBN, the cosmological model is very, very solid, very solid in its prediction, because then it's all consistent. There is no degree of freedom in this, and it works. Except for the lithium-7, of course, it's a huge problem. But if we forget about that, we can say that BBN works. So the question is, it works because we've put a lot of effort in the theory to produce these blue lines, and whenever we make a mistake in a theoretical prediction for the blue line in deuterium and helium-4, then we will be tempted to say, oh, it does not work. It's just because we need to have predictions which are as good as the precision in the baryon bodons, so 1% from Planck, and from the observation of helium-4 and deuterium, which are also 1%. And in order to reach these predictions, the theoretical prediction of abundances, there are many, many things which have to be taken into account, and this is what has changed compared to BBN a long time ago, where things could be predicted up to a few percent. So the first thing is that we need to solve very precisely the plasma thermodynamics. But it's usual thermodynamic with Fermi-Dirac distributions. Neutrinos, electrons, positrons, all this have a Fermi-Dirac distribution function. We know the energy density, the pressure, the entropy. So there is a very clear way to get the temperature as a function of the scale factor just from this. Now, if we have done this, we have 3 steps. Once we have solved for the plasma thermodynamics, we can put this in the Hubble Friedmann equation and get the cosmological expansion, and so the time as a function of the scale factor. Then we need to compute very precisely the weak rates, because I told you that they control the number of neutrons which are left, the time at which there is this freeze out. And so it's essential to control exactly these weak rates, because this is only what determines the final abundance of helium-4. And then for all the other species, we need to control, of course, the nuclear rates, and this is more nuclear physics problem. For the cosmological evolution, it's very simple. You just put all the species which are relativistic. You put this in the Friedmann equation, and you get the scale factor. There is nothing complicated there. Now, if you want to refine this, the only thing you need to do, you need to take into account that since you have a plasma of electrons, positrons, and photons which are coupled, you cannot say that the Fermi-Dirac distribution, that they have independently a Fermi-Dirac distribution. They have some interactions which modify their energy density and their pressure. So typically, their interactions are, if you want to talk in terms of Feynman diagram to see it, the vacuum propagator of the photon is modified by the fact that you have this propagator where a photon can interact with an electron or positron from the bath, and then it can re-emit with the same momentum in the bath. And the same for the propagator, or the vacuum propagator of the electron-positron. They are modified by the fact that they can absorb and re-emit photons. So this changes slightly the pressure, this changes slightly the energy density, so this changes slightly the expansion history, and I told you that it's very important to know exactly the expansion history, because then it controls the amount of beta decay we have between the freeze-out and deuterium production. We have other effects. I'm going to be very, very brief on that. There is this assumption that the electrons and positrons, when they annihilate, they fully annihilate into photons, but then we can take into account that there is a small part of these electrons and positrons which annihilate into neutrinos and antineutrinos. And there is a whole literature, which is rather complicated, about these things, because then it involves the neutrino oscillation, neutrino masses, and so on. So just finding exactly what's the influence of these types of reactions on the neutrino temperature and how it affects also the ratio between neutrino temperature and photon temperature, because whatever goes in this direction does not go in this direction. So you see the neutrinos are indirectly coupled to the photons. Also, this is a modification which needs to be taken into account. Then for the weak rates, there are 2 major types of modification of corrections which need to be taken into account. First, we have finite nuclear mass effects. The fact that it's very simple to compute the weak rates if you assume that the neutron or the proton have an infinite mass, because then they are at rest before interaction, they are at rest after interaction, so it's very easy. The kinematic is very easy, and you have just a one-dimensional integral. But of course, this is not true, because when you do this, you make an error which is of the order typically of the 0.1%. At least if you estimate the error, you would tend to think it's 0.1%. And what we can find is actually you make an error of order percent if you do that. And then you have all the radiative corrections, which are of the order of the fan structure constant, and which are also typically of the order of 1%. Then what's the physics you need to put for these weak interactions? Typically, the vertex of the weak interactions, which transforms neutrons into proton while transforming, let's say, for instance, neutrino into electron, is this thing that you take in the limit where the propagator of the W is completely dominated by its mass. So it's the Fermi theory of weak interactions from the 30s. But here, since a neutron is not an elementary particle, then you cannot just say that it's a left chiral coupling, like for instance, for neutrino and electron. You have this GA, which is an axial current coupling, which is something you need to measure. It's not known from fundamental principle. And you can also put these things, which is called weak magnetism. So you have these parameters. This is known because it's related to this is known, it's related to the magnetic properties of the proton, but this is not known. So it needs to be taken into account, and it adds to the issues we have in knowing the weak rate. Then How do we compute in a very simple manner the weak rate? We are saying that approximately, since the energy transfer between the neutron and proton is completely dominated by the mass difference. So we're saying that whenever we're transforming a neutron to a proton, then we have 1.3 mega electron volt, and basically we are ignoring the kinetic energy in the neutron and the proton. This is true only at the lowest order. Then you need to take into account corrections. I'm not writing here the corrections, but if you take into account these corrections, then this is exactly what I call take into account finite nuclear mass corrections. If you don't take into account these finite nuclear mass corrections, the lowest order you get for the weak rate, for instance here the weak rate for neutron transmitting to proton is this. It's some constant times some one-dimensional integral on the distribution function. So it's a very simple, you see it's one-dimensional. Here it's on the momentum of electron. But the constant in front depends on the Fermi constant of weak interactions, on this axial current coupling, which we don't know, at least, I mean, it's been measured, but it's, and on this Kabibo-Kobayashi-Masakawa angle, which is the coupling between the up and down by weak interaction. And this is also something which is measured, but which is not known with exquisite precision. So the Born approximation rate, they decay with the temperature, so time is going from the right to the left. At some point, they become smaller than Hubble rate, so that's when we can say that there is a freeze-out. It's around 0.8 MeV. Whenever we modify this due to the corrections I discussed, then we're going to change the time at which the rate crosses the Hubble rate, so we're going to slightly delay or anticipate the freeze-out, and so this is going to change the amount of neutrons which are left. Typically, the finite nuclear mass corrections, so these are relative corrections to the rate, as a function of temperature, so time is going from there to there, and freeze-out is around here. And you see that the relative corrections are of the order of 1%. So it's, I mean, the naive estimate would be 0.1%, but then you find that putting all the numerical factor, that it's 1%. Then you have relative corrections. I'm going very quickly on this thing. So typically, they can be interpreted as coming from this Feynman diagram. So you see you have two vertices with the QED vertex here, here, here. You can compute them. This has been done, of course. This has been very well known because you also need to do that when you want to compute with great precision the neutron decay. If you put the neutrino on the right-hand side, the reaction you have is the neutron decay. And this has been studied since the 40s, the 50s, and so. So these are very important questions, but which are known in the literature. And taking them from the literature and putting this in a cosmological context, you find that the relative variations of rate due to these relative corrections around the time of freeze-out, which is here, is of the order of 2.5, yes, 2.5%. So it's really important. These are actually the dominant source. This is the dominant source of corrections that you need to take into account for BBN to work. You have other types of corrections, true photons emissions, finite temperature corrections. So I'm skipping over this because they are not important in the sense that they have a negligible effect. But what is important is the total corrections. You find that the total corrections around the time of freeze-out, which is around 1 MeV, so around 10 to the 10 Kelvin, are the order of, let's say, 4%, 3.5, let's say, yes, 3 something percent. So it's rather large, and you can show that a 3% modification of, let's say, 4%. A 4% modification of the rates changes the final abundance of helium-4 by 3%. So you see there is a 75% transfer between this modification and the modification in helium-4. So it's really important. Now, I told you that whenever we compute the rates, in front of the integral, we have these constants, which depends on the constants of physics. So there is a Fermi constant, and also there is a Kabibo-Kobayashi-Masakawa angle. This, if you take the latest data from the particle data group, the Kabibo-Kobayashi-Masakawa angle is 0.97420. But what is great is now it's known up to 10 to the minus 4, so with a precision of 0.01%. So in some sense, the issue on this constant is not coming from there anymore. Then, in the past, if you look at BBN papers, at Weinberg's book from the 70s and so on, in the past this was very poorly known. I mean, it was 1.2 something, 1.3. So because this was poorly known, instead of using the poorly known value for this, we're using the neutron lifetime as a proxy to determine this constant. Because you can also show that this constant, which is in front, is related to the neutron lifetime here, tau n, and by some numerical constant. So if you don't know this, then you could use tau n. But now, if you look at the latest value from the PDG, particle data group, you find that this is known with some precision, which is rather good, 0.1%. Now it's 1.2755, which means that you could, if you want, ignore the neutron lifetime here and just put GA that you have from the PDG, the Kabib-Kobayashi-Maskawa angle, and you would have a value for the K. But you could also play the historical, yes, 5 minutes. You could also play the same game as we used to play, say, oh, I don't know what are these values, and I'm going to use the neutron lifetime. Okay, so you open the PDG, the particle data group, and you see that the neutron lifetime posterior, or I don't know, the distribution of the probability for the value is like that. So it's really not a Gaussian, it's ugly. And the reason why it's ugly is because there are two types of experiments. Don't ask me many questions on that, but there are essentially two types of questions for measuring the neutron lifetimes, which are beam experiments and bottle experiments. Some are measuring the neutrons which are left, and some are measuring the neutrons which have decayed. And the beam experiments are essentially these ones, which are giving this peak, and the bottle experiments are these ones. So here, these are only the latest values from let's say, the last 20 years. And so you have just one experiment, which is a beam experiment, which is there. And so you see, some type of experiments they keep having 888, and some other types of experiments, they keep having 880 or 880 something. But the thing is that if you use 888, this consistency relation does not work anymore if you use the Kabib-Kobayashi-Maskawa angle and the GA from the PDG. So it means that one of the type of experiment is giving 880 and is very consistent with this consistency relation. The other type of experiment is giving a value which is different by 1%, but which is not working. So there has been some papers, of course, by people working this type of experiments, arguing that we should somehow not trust these experiments, or at least either there is a problem with the experiment or some new physics, and we don't know. But they recommend to use only the values which are here, and this gives a neutron decay rate which is 879.5 seconds. If you put that, then it's fully consistent with the value of GA and the Kabib-Kobayashi-Maskawa angle. Once you have this, it means that you see the precision is very good now. It used to be a lot more. Now you have 0.8 seconds in 800 seconds, so it's a 0.1% precision on the weak rate, which means that it's going to transfer into a 0.1 precision on helium-4. So for helium-4, it's completely, the uncertainty is really just this. The uncertainty is really just this uncertainty. So helium-4, it's done. We control the weak rate. We have all the corrections. We know how much neutrons are left. We know what goes into helium-4. There is this 0.1% error which goes into helium-4. Now for deuterium, other species, then we have nuclear reactions, which are essential because there are only traces of deuterium, only traces of yttrium-7, and so on. But the thing is that now we have the cross-section have been measured and remeasured by various groups for all types of reactions. You have essentially 3 reactions which are important for deuterium. DDP, so deuterium plus deuterium gives proton plus something, deuterium plus deuterium gives neutron plus something, and deuterium plus proton gives helium-3. They have been all measured with a precision of, say, 1 point something, which means that now you have a final precision which is of the order of 1 point something on deuterium as well, which is good because it's also the precision we have on the measurement. It's not working. Okay. So this is about the predictions. Now that you have the predictions, I told you that this is that barium abundance is measured by Planck. But you could say, okay, let's forget that the barium abundance is measured by Planck, and let's see if I can measure it independently with BBN. And since you have really essentially 2 numbers, deuterium abundance and helium-4 abundance, instead of measuring just the barium abundance, you can say, okay, I will want to measure something else, and what you can measure is the number of relativistic degrees of freedom, precisely because I told you that it affects the cooling speed, and so it affects the number of neutrons which are decreased by neutron beta decay. So you can do a 2-dimensional plot with just BBN, which is the red part, and you have this kind of ellipse for barium fraction and number of neutrinos. Then you can combine this with Planck. Of course, you get something which is much better. You can marginalize, and you get a posterior for the number of neutrinos, or the number of relativistic degrees of freedom, and for baryons. Of course, the final conclusion of that is that it works very well with CMB, so this is very important. It's consistent. We could have massive problems, and we don't. But also what is very important is that it's probing very different physics and very different eras. This number of neutrinos the physics behind it is completely different from the physics behind CMB constraining the number of neutrinos. And still, with that, we find that it's around 3, and if we believe it's an integer, then it's definitely 3. So this is a nice part of BBN, is that now we're able to say that it's completely consistent with the CMB up to this small but actually huge caveat, which is lithium-7. And I thank you very much.
Thanks very much, Cyril. Any questions?
Of course. Yes? What? No?
You
I know.
mentioned lithium on your plot at the beginning. Could
Yes.
you summarize whether it's a real problem now or not, what the situation is?
Yes, it's a real problem now. Because now we are, all the reactions which are, where is it? Well, the reaction. Now all the reactions which could affect, so lithium-7 is actually a beryllium-7 problem, because beryllium-7 is decaying into lithium-7. So the plot we have here, just for everybody, so you have one curve for lithium-7 and one curve for beryllium-7. And so since beryllium-7 is going to decay eventually into lithium-7, actually the problem is going from beryllium-7. And so all the reactions have been measured and remeasured. So for instance, the latest reaction which has been remeasured is this reaction. Beryllium-7 going to plus deuterium gives, I forgot what, and 2 helium-4. And this could be a possibility to remove beryllium-7, and then if you remove beryllium-7, you solve the problem. But this as well has been remeasured, and so all the reactions have been remeasured. This one, there is also the reactions which are transforming beryllium-7 into lithium-7. You could say it doesn't matter because I told you that the final product is the sum. But if you do that around that time, if you modify this reaction, when you transform beryllium-7 into lithium-7, lithium-7 then is destroyed. So if you modify this rate, you could somehow solve the problem, but the problem it has so people have seen that, so they have remeasured this rate, and also they find that they find a rate which is not enough to destroy beryllium-7. Then you have other possibilities like adding extra neutrons. If you add extra neutrons, then you can enhance some reactions which are destroying beryllium-7. But if you do that, in the past, if you look at papers just 10 years ago or 8 years ago, it was still possible to do that because if you add neutrons, okay, you can remove beryllium-7 and create lithium-7. But you would also change the production of deuterium. But now we have such good constraint on deuterium that we cannot play with these extra neutrons. I mean, if we play with these extra neutrons to somehow lower the value of beryllium-7, then we lose the good constraint we have on deuterium. So somehow the problem is much worse than it used to be. Yes.
What about measuring the rate? Is one sure that this is the primordial rate, or because there could be destruction in stars? It's 10 to the minus 10. It's a small number.
As a cosmologist, I always tend to to think that the measurement coming from stars is bad. This was before I discussed with people doing the measurement. And of course, lithium-7 can only be destroyed in stars, and it's measured. So contrary to helium-4 and deuterium, lithium-7 is measured in the outer layer of stars. And so you have to believe that it's not affected by the evolution of stars, where, for instance, deuterium is from quasar absorption, so it's much more pristine. So if you think it's not affected by the evolution of stars, and it is, since it's only destroyed, then it means that what you could measure should only be lower than a primordial value, and what you measure is lower. So you could say, okay, that's the thing. But then the measurement is not just that you have stars and they measure the lithium-7 abundance. They measure lithium-7 abundance as a function of the temperature of the stars and as a function of metallicity, and they find a plateau. So it means that for all types of stars, all types of masses, all types of metallicity, they find that there is a plateau. So if there was these things due to like evolution which is depleting lithium-7 because it's burning it, you would expect that there would be a temperature dependence or metallicity dependence. The fact that there is a plateau, when you discuss with people doing the measurement, that's why they are confident that lithium-7 is not destroyed. They say, if it was processed in the center of the stars and then with convection put back into the outer layer, we would not have a plateau. It would depend on the amount of convection and so on, so it would depend on the temperature. So they are really confident that the plateau makes their measurement solid. But personally, I think everything has been tried with lithium-7, so yes, I would be tempted to say it's a measurement problem. Yes.
You point the finger to what?
To what? To the measurement. It's just that maybe the fact that it's a plateau is not. It's an argument, but it's not a final proof that it's not processed. Maybe it's processed in a way which is in the same way for all temperatures of stars, or in the same way for all metallicities. It's yeah, astrophysics, of course.
Okay, well, let's thank Cyril again.
Okay, thank you very much. teach. So I cannot stay for it to actually ask for permission to be here. And so now I have to switch. Okay. Oh, I'm so sorry.
He wanted to come and talk.
Okay, so our next speaker is Ruth Durrer, and she's going to tell us about theoretical challenges in large-scale structure.
Thank you for inviting me to talk here. I can't do it. Okay. Can you hear me? Yes. Yeah, it's a bit easier if I, okay. Okay, I will talk about theoretical challenges in large-scale structure. I will not talk about n-body simulations because we will have other talks about this topic later on. So my talk is, after a short introduction, I will talk about what are cosmological observables briefly, and then a bit about the angular power spectrum of galaxy number counts. And I want to especially stress that this is an alternative path to measuring the lensing potential, and that will be possible with future high redshift wide-angle surveys. Then I will talk briefly about the correlation function, which is sometimes easier to deal with than the angular power spectrum, and go beyond linear theory. Okay, you all know fluctuations of the CMB are small, and we can treat them within perturbation theory. And this is no longer true with fluctuations of large-scale structure. They become very large on galactic scales. Galaxies and their formation are not only affected by gravity, but there are... Oh, is it off? Oh, hold that. So let me try to fix it on this. Maybe that works. Okay. And if we, on smaller scales, of course, electromagnetic and nuclear interactions are relevant for galaxy formation, star formation, etc. And if we think of all the physics which goes into it is nonlinear physics about over 36 orders of magnitude, which govern from the universe from stars to the Hubble scale. So clearly, a brute force approach is impossible, but we have to resort to other ideas. What we do in cosmology mainly is, first of all, using effective theories. We hope that we can model galaxy formation and all the non-gravitational physics by some kind of bias expansion, and that we can, to some extent, model nonlinearities, at least on large scales, with some effective theory of large-scale structure, which both require a limited number of parameters, which we can measure either with n-body simulations or with data. If we measure them with data, however, we have to be careful that we do not first measure these parameters with data and then infer our cosmological parameters. We have to do all of this in a self-consistent way, but that's what people usually do. What we, of course, make use of is, as we always do in physics, we make use of the separation of scales. So if somebody wants to study star formation, she will not at all be bothered about the dark energy equation of state or so. Or if somebody wants to investigate the dark energy equation of state, she doesn't care about how galaxies produce their stars. For the rest of this talk, I shall mainly concentrate on scales which are larger than a few megaparsec, where we hope that gravity is really the dominant force, and hopefully the only game in town, apart from some bias factors which relate light to mass, which we still have to study. So let us briefly take a step back and think about some basics of cosmological observations. When we observe something in the universe, usually we use massless or nearly massless messengers, mainly photons in cosmology. There would also be neutrinos and gravitons, but they interact very, very weakly, and we have just started seeing some gravitons from the universe. But in cosmology, we are so far mainly looking into photons from visible to radio wavelength. When we look far away, we look into the past. This is a challenge, but of course also a blessing. We can see our past. But we have to be careful, namely all our observations which we make them on our perturbed background light cone. So if we do cosmology on large scales, we really have to take into account that, for example, the density fluctuation at some hypersurface of constant time is not an observable. Or the power spectrum, which was plotted several times in this conference, is not truly an observable. And of course we can, so if we see a power spectrum and an observer comes to us and says, I have measured this power spectrum, she has always made some theoretical modeling, because in cosmology, what we really see, as it was mentioned several times already in this conference, we can only see angles or directions and redshifts, or if you want fluxes or something like that, some distance indicators, but we never measure distances. If we can infer distances using a cosmological model. For small surveys, this is all not very relevant, and since a long time we are used in cosmology in measuring distances in H inverse megaparsec, because small distances are proportional to redshift divided by the Hubble constant, and so the model dependence through the Hubble constant, we have just increased them in our unit of length. But once we go to redshifts of order unity, this is no longer enough. The dark energy equation of state enters, and all these things which we want to measure actually enter in our distance. So what we truly measure is we count the number of galaxies in some direction n and in some redshift, at some redshift z, and we look at the fluctuations of this count. And this depends on the density and on the volume. And this quantity here is really a measurable quantity, and we can determine its correlation function, which by statistical isotropy should only be a function of the angle between the two directions. This observable quantity has been determined to first and lately also to second order in perturbation theory, and the first order perturbation theory references are given here. That's how it looks. It contains, of course, the density here in co-moving gauge, and in linear perturbation theory we hope that this is only modified by some bias parameter, which of course depends on redshift, but hopefully not so much on scale. And the other term which we all know and is taken into account in most measurements is redshift space distortion. But there is another term here which comes from magnification bias. Actually, this term S is the logarithmic derivative of the galaxy number density at the upper edge of my survey. This magnification bias here comes from two terms. There is a factor 2, which comes from the fact that if I have lensing, I infer a larger area than what is actually there, so I underestimate my density. On the other hand, sources are magnified and can make it into my survey. Sources which wouldn't make it into my survey if they wouldn't be magnified can make it there, and that's this term S, which depends on my instrument, how what is the faintest magnitude which I can still see. So this is the logarithmic derivative, and this range factor of 5 here comes from the definition of magnitudes. So these redshift space distortion or Kaiser term and this magnification bias term are the most important terms, are the only ones which scale with wavelengths actually like the density. They are of order k over h squared times the gravitational potentials. All other, where k is the wave number, all other terms which appear here are actually smaller and can be neglected on scales which are well inside the horizon, on harmonics which are larger than 10 or 15 or so. Here you see a relatively old image of redshift space distortion. I'm not going to discuss it. It has been discussed several times during this meeting. Since we now measure this overdensity in directions and as a function of redshift, we can expand it in spherical harmonics, and all becomes much more like the CMB, except that we now have CLs which depend on two redshifts, the two redshifts of the two kind of pixels which we are correlating. Here you see one plot, for example, for very small redshifts. You see the only really important term is the density term, and a little bit comes from the redshift space distortion, and all other terms are kind of negligible. If we go to the other extreme, we have a very high redshift and a wide redshift bin. Suddenly the lensing term actually becomes dominant and is very important on all scales, and can by no means be neglected. What we looked at here is something a little bit more realistic. Namely, we were looking at Euclid and SKA surveys and looking at their magnification bias, predictions for the magnification bias and for the bias as a function of redshift, and we're looking what happens if we correlate different bins. So we were considering the full CLs, only the local ones which are more or less density and redshift space distortion, and correlating the local with the lensing one, and adding also the lensing correlated by itself. You see, if we correlate bin 1 with itself from the Euclid photometric survey, we see only the local term. However, if you correlate bin 1 with bin 4, signal goes down significantly, but we see significantly also the lensing term. So the total here is much lower. If we do the same thing with SKA, correlating bin 1 and bin 4, we only see the lensing term, and the local term is completely gone. The reason for that is SKA, we have very precise redshifts, so there is no kind of contribution from the lower bin into the higher bin as we have it with photometric redshifts. So the density term is completely gone with these precise redshifts of SKA, whereas in the photometric redshift bins for Euclid, we have to correlate bin 1 with bin 10 to see such a clear lensing signal. Now, can we actually use this observation of the lensing signal of kappa to measure kappa? Our answer to this in this paper is yes. We made a very simplistic analysis where we were just multiplying the lensing signal with some factor beta. That would be like the A lens in the temperature fluctuations. And we were doing a Fisher matrix analysis of a Euclid-like survey. let me just show what we are most interested in, namely how well can we measure beta. You see we can measure this beta if there would be such a modification of gravity by a couple of %. And this beta would be a simple combination of the sigma and mu, which Alessandra introduced this morning. So we could measure here some modifications of gravity. And you see we could measure it with a similar precision as other cosmological parameters of a few %, or on the % level. What is interesting is if one takes into account only autocorrelations, that's the dashed lines, then you see for most parameters, if one takes into account only autocorrelations, as for the 10-bin configuration, there is no big difference. Whereas for the beta, it's very important to take into account the cross correlations, which are the solid lines. And it's no big deal whether you have 5 or 10 bins. So that is quite intuitive. Here, the lensing is very broad, and whether we have 5 or 10 bins doesn't really matter, but it's dominating the cross correlations. So we need to have cross correlations to determine it. Another thing is if we neglect this lensing, what can happen? If we say, okay, we see our catalogs actually have the lensing in it because they have all the physics in it, and we analyze them pretending it wouldn't be there. What happens? Here, this is a MCMC estimation for a Euclid-like photometric survey again with these collaborators, and let us concentrate only on what happens to the neutrino mass. You see, if we make the correct analysis with lensing, we have the red curves, and we see the input neutrino mass and with considerable error, right? The input sum of the neutrino mass was the lowest possible value, 0.06 electron volts. But if we assume there wouldn't be any lensing, we get these curves. Even if we say, okay, in autocorrelations, lensing is totally subdominant. There we might neglect it. We still get we discover a high neutrino mass where there actually is none. So in a survey like Euclid, even if you are not interested in lensing, you cannot just ignore it. So what I want to highlight here is that we can actually use this lensing, this completely alternative way to measure the lensing potential, which has nothing to do with shapes of galaxies and has its problems and systematics, but they are very different. We can use this to test, for example, general relativity. One possibility is given in the EG statistics. You probably all have seen the poster by Basundara Ghosh, which studied on how this EG statistics is affected by lensing of foregrounds and can be corrected for it and can provide a nice test of general relativity. And you will also hear tomorrow an interesting talk by Mona Jalilwand, where she will talk about combining number counts with intensity mapping. Intensity mapping doesn't have these lensing terms. So intensity mapping, since lensing conserves surface brightness, there is no lensing term in intensity mapping. Like in the CMB, there is no lensing term at first order. For intensity mapping, it's the same. And so the possibility to measure this lensing potential with galaxy number counts, I think, is now becoming relevant and hasn't been so in the past, but this will happen and will present an interesting alternative to shear measurements. Let me talk about the correlation function. We don't have only photometric redshifts, but we will have extremely good spectroscopic redshifts. Now, if we wanted to make thin redshift slices of roughly this, of something comparable to the resolution of a spectroscopic redshift survey to analyze the data for one set of cosmological parameters, that would be 1 million CMB spectra, and to do an MCMC for each value of 1 million spectra is kind of unfeasible. So furthermore, there would be very few galaxies within the exact redshift range of this value, and we would have a huge, which leads to a huge shot noise in these CLs. So this might not be the best way of looking at it. So it might actually be better to study the correlation function. What I think might be a good idea is to make relatively thin redshift shells with a resolution of maybe 0.1 and study the correlation function inside these redshift shells and correlate these redshift shells with the CLs. This would certainly be much more feasible. Now, to define the correlation function, including all the relativistic effects, a simple way we have found is to define the parallel distance between two redshifts just as the distance, difference between the co-moving distances, and then introduce the angle mu as the ratio between this parallel distance and the full distance. You can translate this into an angle which is very close to this angle gamma or beta, which are often used, which split either the two lengths here by 2 or the angle here by 2. The differences are small, but non-zero. And it's very easy if you have this correlation function in terms of these variables to convert it, for example, into the variable cos gamma or cos beta, if you like this better. What we have seen by computing this correlation function is, first of all, that the wide angle effect, which some people have taken into account, are really of the same order as the relativistic correction. So it is inconsistent to consider only the wide angle effects and not relativistic corrections, or vice versa. They have to be studied together. And here what you see, let me just concentrate on the lensing term again. You see that at mu of 0.8, it is quite small, less than 1%, whereas when mu comes very close to 1, it becomes very important, and at mu equals 1, it's dominating the signal. This, you can see it also here, that on larger scales, it's more important, of course, than on small scales. You can also look at the multiples of this correlation function, and this is at redshift 0.1, this is at redshift 1. At redshift 0.1, it's a small effect and can more or less be ignored. But at redshift 1, if we want to go after the hexadecapole, we need to include lensing for sure. What is interesting also is that lensing gives us a series of higher multiples. We have computed them up to 2030. They are all similar, because the multipole decomposition is maybe not the best thing to do, because this lensing is so much peaked in forward direction. Here we have seen that you can also get a reasonable signal to noise in the lensing signal inside just one redshift bin of 0.1, or inside redshift bins. Here, correlations between different redshift bins are not included, and you still get a signal to noise, depending on what your survey is, but not so much depending on the number of redshift bins which you use. This has been computed with a public code, which you all are invited to use by my student Goran Jelinek. Let me go beyond linear perturbation theory. That is the second order expression for the relativistic number counts, which has been computed by 3 groups. And in the meantime, we'll know at least that the first and the last group do not quite agree with all the terms. But things look bad. But you see, the advantage of these number count expressions is they never use Einstein's equation. They only use that photons and dark matter move on geodesics. If that is not true, these expressions are not correct. Otherwise, they should be. And what is also nice about it, if you only want the dominant terms, if you say, I'm not interested at L equals 2 to 10, because there I can use linear perturbation theory, then this boils down to this expression, which is really handy and can be used. You see, I mean, all the density and velocity terms, they have been computed long ago to arbitrary high orders by François and others, by Francis Bernardot, and we of course agree with them. But there are new terms which come from lensing and which come from more or less the determinant of the lens map to arbitrary order. And we can give a kind of a relatively straightforward recipe how to go to third order, to fourth order, and so even though it's a bit painful, it can be done. If you want to calculate the density or number count to second order, you have to go at least to third order, right, to get the correlation between first and third order as well, and not only second order squared. But what we have done is we have looked at the bispectrum. These are the Newtonian terms now in L space. You see something that they decay here is L. They decay very rapidly if redshifts become different. But if you, what you also see is if you look at the density and the redshift space distortion, that they have very little shape dependence. The shape dependence between the squeezed limit and the equilateral limit is on the order of 10%, and the same for the redshift space distortions. What is interesting is the lensing term stays on if the redshift difference becomes large. Here, this is correlation of density with lensing, and here you have at very close redshifts, the bispectrum, reduced bispectrum as a function of L. At very close redshifts, it's the Newtonian term which dominates, and if you go to big redshift differences, it's clearly the lensing term which dominates. Okay, this was all I wanted to say. My conclusions. So we all know that we can only observe on the background light cone, and if we have wide-angle deep surveys, this becomes now relevant. We have to take that into account. Magnification bias actually provides us a new way to measure the lensing potential, which is alternative to shear measurements. Wide-angle effects and relativistic corrections are of the same order, and they cannot be treated separately, because looking at this correlation function, we really have seen consolations, so it's important to take them into account both. And relativistic effects are relevant only on very large scales, but careful there, they actually are quite degenerate with bias dependence from primordial non-Gaussianity. So if you are interested in that, you have to take them in. And perturbation theory of the full relativistic number counts can become cumbersome, but the dominant terms, the terms which scale like the density fluctuation, can be computed by a relatively well defined procedure. Thank you for your attention.
Thanks very much, Ruth. Any questions, George? A microphone's coming.
Yeah, thank you for a nice talk and beautiful work. Can you go back to slide 4?
Mm-hmm.
Next one. Yeah. Slide 4.
Oh, sorry.
Yeah. What we truly measure is delta n as n minus n bar over n bar. That's gauge dependent.
My n bar is the average which I make with my observation. You know, I didn't say it, But if I make a bar, this is a spherical average, and if I make, this is an ensemble average. So this is really measured, right? I measure in my small redshift slice, I measure n in all directions, and I subtract from it the mean over the entire sphere. That cannot be gauge dependent. And actually, we calculated this for an arbitrary gauge, and we found that all the gauge-dependent terms drop, and we can write it fully gauge independently.
Okay, so n bar is not a background model. It's
no. N bar is not a background model. It's a measured quantity. Redshift is the measured redshift. All this is quite important. Yes?
Okay, we'll have the other George.
So Ruth, once you're sensitive to magnification biases, so you have to worry about the image processing, right, and how fluxes are defined and so on. So I just wondered how sophisticated has been your model?
Yeah, that's a very good point, of course. I didn't really talk much about this factor S, right, and all depends on that. For example, if your experiment is such that it measures the entire flux of the galaxy, or let's say your experiment is sensitive to surface brightness, then S is 0. So you can drop the S. But that would be even better, because usually S and the factor 2 in front, which is purely geometrical, which comes from the transverse magnification of the volume, and S enhances your number, and the magnification of the volume makes it smaller. So, for example, we have modeled what S would be for Euclid. I don't know how good our modeling of this is, but there we found at redshift roughly equal to 1, the factor 5S and 2 exactly cancel. So at redshift roughly equal to 1, Euclid is like an intensity measurement. But if you go to 1.5 or if you go to 0.5, which will be there in the photometric survey, there S is considerable. If we modeled it correctly. I mean, yeah, we assumed that what you see is really the magnitude of a galaxy, and it's sensitive only to the magnitude. If it measures surface brightness, there is an entirely different story, and I must agree, I don't know how to do this correctly.
I'll take one final question from Joe.
So in looking for primordial non-Gaussianity, how low can you go before the relativistic effects come in and mess that up?
You're talking about the scale-dependent bias. Yeah. They come in exactly the same way. I mean, if you look at the derivation, it's exactly this factor 1 over hk squared, which makes the scale dependent of the bias, which is also these relativistic effects. It depends now if you use multi-tracer, then you can have relativistic effects which come in and produce you a dipole even, which are much larger than those. The thing is that the redshift dependence is not exactly the same. So that can help. If you measure it in one redshift slice, there is perfect degeneracy. But if you measure several redshift slices, the redshift dependence is not the same for the bias dependence and for the relativistic terms in the number counts.
Okay, well, let's thank Ruth again. Okay, so our next speaker is Daniel Gruen. He's going to tell us about dark matter and the CMB.
All right. I'll try not to keep us from our lunch too long. It's a pleasure to be here, and thank you for the opportunity to tell you about dark matter and the CMB. I, too, was given my title, so I'm going to start with a pretty broad review of dark matter candidates, and then I'm going to do a deep dive into my personal favorite, the ultralight axion, and I'm kind of going to try to interweave current constraints with the possibilities of future CMB experiments. So we know from the CMB and the delegate interplay of gravitational redshifting, infall, and radiation pressure that we can measure the matter density of the universe. This animation is shamelessly stolen but attributed. And now that we live in the era of accurate cosmology, we have these extremely precise measurements of the multiple moments and also the weak lensing power spectrum of the CMB. So rather than just fitting parameters better and better, the question I want to pose is what can we learn about models for what the dark matter might be? It's worth a reminder that another possibility is modified gravity. MOND has a bad name, probably for good reason, but the Tevis theory, which might be described as elegant, gives you at least a framework for explaining things without a non-relativistic dark matter, but it misses the second peak. But I'll be very interested to hear 70 years from now, when we still haven't found dark matter, I hope not, if there is a nice theory, a relatively nice theory that can fit the peak structure of the CMB. One of the big themes in the results I'm going to present is the constraining power of microwave background lensing. CMB photons propagate from a source plane at redshift of 100, and the lensing deflection angle, which of these buttons is the lensing deflection angle here, depends geometrically and also through the growth of the potential on new particle species in the universe. So that a lot of the results I present will connect up with that. But in the era of precision cosmology, we have this nice accounting of the energy budget of the universe, in some cases, with three-figure precision. But perhaps a depressing way of looking at this is just accounting, right? So what can we learn about the interactions and the detailed dynamics of these dark degrees of freedom that we haven't measured yet? Here's a nice mind map made by Tim Tate of all the different possibilities for dark matter. And when I was given a review talk, I was initially terrified that I had to hit all of these. But then I realized that review talks are an exercise in omission, so I'll be committing many sins of omission. And if I didn't cover your favorite model, ask me about it afterwards, or I even have a few backup slides. So here's a nice summary of some of the dark matter candidates. I'm going to be talking about ultralight axion dark matter, and then WIMPs and the light dark matter candidates. I'm going to take a pass on this higher mass range here and focus on a variety of possibilities here. So the classic WIMP miracle is just this idea that an annihilating WIMP freezes out and has some relic abundance. This is kind of the standard relic abundance expression. And so a lot of effort has been devoted to trying to find this WIMP. One realization of the WIMP, of course, is in supersymmetric extensions of the standard model. There are many varieties. The neutralino is one popular possibility. And there are a variety of direct detection experiments trying to use nuclear recoils in germanium crystals or supercooled xenon to try to detect dark matter directly. And here's kind of the state of play of experiments right now. We have increasingly tight upper limits, which in principle rule out the only claimed detections by DAMA. And we have, in the last few years, seen an appreciation of the fact that cosmic ray, supernova, and solar neutrinos set some kind of floor to the lowest the lowest scattering cross-section we can measure. The CMB has also offered some interesting constraints. People in this room know far more about this particular exercise than I do, but this series of lines right here shows you what limit you get on the thermally averaged annihilation cross-section depending on the precise branching ratios that you use. And the nice thing about the CMB here is that the constraints extend to fairly low masses and again offer critical tests of things like the AMS excess and various excesses that have been seen in Fermi. But there's been some really nice work recently by John Beacom and Rebecca Lean saying, these relationships between cross-sections are fundamentally model dependent. So if we just include all the CMB and gamma ray limits right here, considerations from quantum field theory and closure arguments in the early universe, there's actually this nice triangle in parameter space where the WIMP is still allowed. So the WIMP is not ruled out. Take-home message number one. And there's also thoughts that the point source subtraction due to pulsars in recent work has actually been overly aggressive. So there is still room for WIMP dark matter. But if we want to go to lower masses, we have to introduce a new light mediator, perhaps with some kinetic coupling to the standard model. And the interesting thing is these mediators would be produced thermally in the early universe and contribute to an effective. So experiments like CMB stage 4 are actually going to be very powerful at testing some new decoupled dark sector where a new light degree of freedom mediates interactions. These models also predict that there should be scattering between dark matter and baryons. And so here's a figure from a nice paper by Cora Dvorkin where we see the experimental limits. And the real feature of the CMB here is it's going to go to much lower dark matter masses, the current direct detection efforts. And here's kind of the lay of the land in terms of going from Planck to a futuristic CMB stage 4 type effort. We can improve our limits to the cross-section by up to 2 orders of magnitude. The basic physics is you have an additional damping due to just an additional term in the baryon velocity equation of motion for the CAMB aficionados in the audience. And the interesting thing here is if you look at a 1 GeV dark matter particle, do the constraints for some fiducial model with lensing in the peak smoothing, and then include the trispectrum analysis. Lensing can really break the degeneracies between different microphysical models. And that theme is going to persist through this talk. Thinking even further into the future, if we're ever so fortunate as to have another CMB spectral distortion measurement, Yassin Ali Hamoud and collaborators have shown that you get nice opening up of parameter space due to interactions between dark matter and other degrees of freedom. But it wouldn't be a talk by me if I didn't get to talk about axions. So let me remind you what they are. The theory of the strong interaction, QCD, has this anomalous theta term, and if we introduce a new U1 pseudoscalar, it can dial this degree of CP violation down to 0 dynamically, and this particle will pick up a mass non-perturbatively, and if it's displaced from the minimum of its potential in the early universe and is not produced thermally, you get a relic abundance roughly given by this expression. For a micro EV scale dark matter candidate, you get the right density. The devil's all in the details of this term, which quantifies things about initial conditions and harmonic terms and how the symmetry related to this new degree of freedom was broken in the early universe. But before diving deep into ultralight axions, I just want to alert everyone to the fact that there have been real changes in the direct detection of axion community. For about 30 years, everybody was either trying to detect axions as they came through a radio frequency cavity or were produced in the sun and then converted back into photons by a dud magnet from the LHC. These are all ideas thanks to the great Pierre Sikivi. And there's now a new experimental effort to scale this up where you take 6 X-ray solar telescopes. Imagine, somewhat surprisingly, the biggest challenge here is tracking the sun, even though it's a large angular size object, because having a guiding telescope pointed at the sun is a non-trivial engineering exercise. But EAXO is underway, and I just want to show you the lay of the land. All the real constraints to axions are like these green solid curves right here. These are limits to the photon couplings. And all these kind of hashed or vaguely transparent things here, these are all new microwave cavity experiments that have been proposed or are underway. There's a completely different concept called abracadabra. Then these X-ray telescopes are actually going to touch the QCD band in this mass range. People used to call this the axion from hell, but I guess it's now become accessible. And then there are completely different detection modalities based on the couplings to nucleons using NMR techniques put forward by this group at Stanford and Johns Hopkins. So a lot of activity. It's really exciting to go to axion workshops. So ultralight axions. The idea comes to us from this notion in string theory that there are lots of extra dimensions, and you end up with a profusion of scalars. And the big idea is that these light scalars, or pseudoscalars, have a mass distribution that scales exponentially with some geometric quantity in the extra dimensions. So you get a very wide distribution of axion masses, very light axion masses in principle. And the cosmology of these things is as follows. At early times, before the field begins to roll, you have something that acts like a cosmological constant. So as we heard from Wayne, there are applications to these types of fields to dark energy physics, but then they coherently oscillate and redshift as dark matter. And so just for the purposes of nomenclature, I'm going to call dark matter type axions that are heavier than 10 to the minus 27 eV. And that threshold is just set by demanding that they start to redshift as dark matter before matter radiation equality. Otherwise, you completely screw up cosmic structure formation. So the phenomenology is basically just a perturbed field moving in a gravitational potential, our good old favorite Klein-Gordon equation. And the interesting thing for these ultralight axions is their de Broglie wavelengths can be comparable to astronomical length scales, leading to some very unusual wave-like phenomenology. This is usually treated by modeling them as a fluid with a scale-dependent sound speed. And if you just go back to your old astrophysics classes, right, there's this good old Jeans instability. And the Jeans wavelength of the axion scales as its mass to the 1 over the square root of the mass. And so this will lead to a suppression in the growth of density perturbations of dark matter that's different from the usual CDM picture. So just to give you an example, here's a given mode, a higher K mode, and this dashed behavior shows the behavior in CDM. And in the axion picture, you have pressure support, and so the perturbation can't grow till late times. So a lot of this physics is included it's based on 2012 CAMB, so I have some homework to do, because CAMB 1.0 just came out, just an advertisement for Anthony, official release. But we shoved in this effective fluid treatment self-consistently everywhere, and analyzed at the time data from Wigglesy and Planck 2013 data. And this is work done with many other collaborators, but the key kind of figures here have been René Klajek, Dottie Marsh, and Pedro Ferreira. One of our key results was this upper limit to the axion energy density. In this middle band, axions are basically kind of dark matter and kind of dark energy, but not terribly good at doing either, right? There's interesting effects in the power spectrum. And when you get to very high or low masses, they become degenerate with standard dark matter or dark energy. One of the more interesting recent developments has been our use of gravitational lensing to constrain these models. So axions would change both the geometry of lenses and the growth of potential perturbations. And here's a plot just kind of showing, with the color bar showing the axion mass and demanding that it be all the dark matter, what the lensing potential power spectrum looks like compared to lambda CDM. So as you dial the axion mass down, you start to see significant deviations in the lensing deflection power spectrum, which tells us, as came up in a more recent paper, that you get significantly improved constraints on omega axion h squared over just using factor of 3 roughly, over just using the primary anisotropies. How am I on time? I can regulate my speed. I'll keep talking for now. Another one of the interesting things about axions is unique among dark matter candidates. They would be a light spectator field during the inflationary era. So they would pick up de Sitter space quantum fluctuations that aren't correlated with the fluctuations in everything else. So it's, classic example of isocurvature. What's interesting is that for these ultralight axions, if the mass is low enough, the isocurvature transfer function is actually significantly changed. So at least in principle, if you're doing an MC, make sure not to say MC a third time, analysis, you have to look at these details in the transfer function. The basic picture here is that you take your favorite CMB measurement, you put a limit on the isocurvature fraction, and if you then saturate this isocurvature fraction measurement, you actually relate the energy density of the axion, which is related to the field initial condition, to the inflationary energy scale. The inflationary energy scale sets the amplitude of the isocurvature fluctuations, but it also sets the amplitude for tensor modes. So if ultralight axion dark matter is detected, with some abundance, inequalities like these give you a maximum value for your inflationary energy scale. So this is bad news if you're trying to measure primordial B modes, although this is a theorist talk, so there are at least 20 novel modifications to the thermal history of the universe you can make to retain detectable B modes even in these axion models. So don't worry, go measure things, let the theorists do their thing. In a later paper, one of the things we did was we actually tried to translate these isocurvature constraints into the language of dark matter Oh, okay, lots of time. I'm going to talk very slowly now. We can remap these constraints into the language of axion energy density here on the y-axis, and then basically a predicted tensor to scalar ratio. So once you fix the density and you saturate isocurvature upper limits, that predicts an H inflation. Once you have H inflation and you fixed AS, you get a prediction for the tensor to scalar ratio. So at higher masses, where you're really approaching a regime where axions are starting to behave more and more like CDM, you make the same predictions for the value of R that you would just for standard CDM. But as you go to lower and lower masses, you actually blow up these contours, and you can potentially have consistent pictures where you have both detectable tensor modes and detectable isocurvature. Of course, these are at very low masses, so something I haven't really said out loud but should is we're really exploring pictures where this particular axion is perhaps one of many components in a very rich dark sector. It's not the dark matter just as of yet, but that's okay because in these theoretical pictures there tend to be many such particles. I should actually give a shout out. There's a nice, well, I haven't seen the poster yet, but I'm sure it's nice because the paper's nice, by Robert, I don't know, Reischke, who examines the kind of different picture where the Peccei-Quinn symmetry is broken after inflation. And the nice thing there is that the isocurvature constraints actually rule out axions, have the power to rule out axions in the dark matter, the straight up cold dark matter part of parameter space. So I definitely encourage you to have a look at that. So now I want to touch on some future possibilities, some work in progress, and some open questions that keep me up at night. And I've been really excited to see lately that they're bothering other people too. So maybe as a community we'll figure it out. So one other really interesting way of testing axions is using the Lyman alpha forest. I'm sure most of you know what that is, but just in case you don't, this is the absorption flux power spectrum of neutral, nearly linear hydrogen clouds along the line of sight to distant quasars. And when you look at the 1D flux power spectrum of these Lyman alpha absorption systems, plotted here in the appropriate funny units, in ultralight axion dark matter models, there's a high K suppression in the matter power spectrum. And you can see that right here if you compare the cold dark matter flux power spectrum at different redshifts. This is from a paper including some hydro simulations by Veer Dissich and Matteo Viel and collaborators. You see this characteristic turnoff in the matter power spectrum. So you can, in principle, use this to stringently constrain the axion mass, and that really pushes you into the 10 to the minus 22 EV part of parameter space. And there's a very rich discussion going on in the literature about whether the effect of axions is adequately captured just by initial conditions in the power spectrum, whether this Jeans length scale and its dynamics is important in the course of the hydrodynamics here or not. And I don't think the answer is really known. But a very interesting point has been made by Takeshi Kobayashi and others, which is you can overlay, so here's the axion mass fraction as a function of the mass, and this red region is what's consistent with the Lyman alpha constraints. And this blue region is what's needed if you want the axion to suppress power enough that it solves the small-scale structure challenges to lambda CDM. And careful not to use the word problems with lambda CDM. So there's kind of this narrow island, right, where the two constraints overlap. So if there's detailed physics of axion dynamics, perhaps related to this effective fluid approach that lead to minute changes in the power spectrum, our inferences about the viability of them as a dark matter model could change. So I'm just putting that up there to get even more people having trouble sleeping at night, I guess, about this. And there's also just now, people who simulate things are just now starting to embrace the idea of fuzzy dark matter and to explore the phenomenological consequences. This is not at all like an n-body simulation. You have to do a full wave-like simulation of dark matter. And in this pioneering simulation by Shive et al., they saw macroscopic, cosmologically sized interference fringes. Numerical artifact, real physics, we don't know. So kind of an interesting opportunity for exploration. Turning back towards things we can test with the CMB, we could ask how that U-shaped contour might change with an experiment like CMB stage 4. We heard all about that, so here are just some quick characteristic numbers. If you want the details, go read the science book or the decadal survey report, which will be out in a few months. But the basic idea here is Any of the big kind of next level CMB experiments under discussion will improve our sensitivity to ultralight axions by about an order of magnitude. And if you really want to push things, we heard, I think from Suzanne, about this idea of a very large dish, small-scale CMB experiment. It's called CMB HD. I'm going to propose that we rename it CMB Deep Dish. Through its tests of weak gravitational lensing of the CMB, an experiment like that could actually test ultralight axions in the regime where they constitute all of the dark matter, and nearly in the linear regime. So that would be a really nice complement to the other ways of looking at things. Just want to feature some of the work by some of our excellent undergraduates at Haverford College. Here's Garrett Farron. And Garrett and I decided to ask the following question. Axions change the growth of structure in the universe, so they should change the pairwise velocities of galaxy clusters. And so because those pairwise, those galaxy clusters do scatter CMB photons, we should change these now famous hand-it-all measurements of the kinetic Sunyaev-Zeldovich effect if all the dark matter is made out of axions. This plot is not looking so great, but in a nutshell, here's the usual CMB power spectrum, the primary anisotropy power spectrum, and here, sort of a series of curves all cutting off at high L. We see a distinctive change in this high L contribution to the power spectrum of the KSZ effect. But the issue, of course, here is that the changes that occur due to axions are all well below the noise floor of even the most futuristic experiments. I'm not an expert on this, but I don't know if that's something you can subtract out if you have distinct shapes. But it seemed a little grim. So the next thing we did is we considered, just shown here for an example, a 10 to the minus 26 electron volt axion, just to show you the constraining power of things here. And the curves I want you to look at are this high green curve, which include halo model type effects. And then that's for the lambda CDM case. And then this blue curve is the axion model. So in principle, the next generation of CMB experiments may also test axions in the right mass range for dark matter using the KSZ effect. And Garrett and I are hard at work on a Fisher forecast. He paid too close attention in my computational physics class, so each power spectrum used to take 30 minutes to run because it used Gaussian quadrature. We've now cut it down to 10 seconds, and so we're ready to do some Fisher matrix analysis. Garrett's applying for graduate school next year, so keep an eye out for his application. Before I wrap up, I do want to tell you about one thing that has been bothering me for a while. Essential to all this work so far has been the use of the so-called effective fluid approximation. So at very early times, we have a Klein-Gordon homogeneous equation, and then here we have perturbations. I've not specified the metric terms because they're different in every gauge. And then at some characteristic joining point where the field begins to oscillate, when m is of order the Hubble parameter, we switch to a prescription where the density redshifts in this way, and then we have the familiar equations of motion for a fluid in synchronous gauge, the one difference being that we have a scale-dependent sound speed here. So with my thesis student now 2 years ago, Johnny Cookmeyer, who's now studying spin waves in alpha rubidium chloride, I guess he decided to go do something useful. But Johnny did a fantastic job writing their own Boltzmann code. And the key here was to not try to embed this into a larger code, but really take something where we can specifically put in as much physics as we need to get a more or less percentish level accurate CMB power spectrum, and just look at the effects of truly solving the Klein-Gordon equation at all times versus this effective fluid prescription. And what's shown in these plots is lambda CDM, various axion models, and then the red dashed line and blue dashed line are two different ways of implementing this prescription where you switch from a field evolution to a fluid evolution at some time. So shown here for 10 to the minus 27 electron volt axions making up all the dark matter. That violates the constraints, but I'm just trying to show you the sense of the effect. You have potentially large, higher than percent level differences between the two ways of treating things. So the thing we wanted to explore was what kind of impact this has on CMB parameter estimation. We computed a bunch of power spectra and a bunch of derivatives, and then we used some very nice expressions for biases, right? When you imagine that you have a Gaussian likelihood and you just have the wrong minimum because of some systematic you haven't put in, there's some nice papers applying this to patchy reionization by Nabila Aghanim and others, and Shimon Itzhaki, where you can predict the implied bias on the axion density as a function of the axion mass when you saturate the limits. I know, a lot of parentheticals there. When you saturate the limits from past work. And so there's good news and there's bad news. The good news is that for a CMB-only type constraint, the bias rises to at most of order a sigma. If we're worried about a detection, we'd certainly sweat the details here. But for upper limits, this is not a huge deal. And I should say this is all. This right plot in particular may change, so stay tuned. But if you actually break the degeneracies with all the other parameters, basically fix all the cosmological parameters at fiducial values, then you get, in principle, even for Planck, fairly large biases in the inferred axion, ultralight axion limits. And so far, this work has just included the primary anisotropies, so it's entirely possible this will become a much bigger effect once we fold in the effects of weak gravitational lensing of the CMB. So to wrap up, future CMB experiments will offer a variety of very interesting probes of dark matter physics, including tests of the QCD axion, ultralight axions, dark matter baryon scattering, and dark matter annihilation. CMB lensing is actually going to play a really big role in disentangling different things that could explain deviations in the primary anisotropies. That probably doesn't come as a huge surprise to many of you. And there are theoretical and numerical subtleties that need to be resolved, perhaps through a Schrödinger type code that will do this all much more accurately without any approximations. Thanks.
Okay, thanks, Daniel. Any questions? Front for Ruth.
Lower mass limits also apply on fuzzy dark matter?
Sorry, say that again?
Do your limits for lower mass limit on the axion also apply on fuzzy dark matter?
Oh, yes. Sorry, terminology thing. I should have said I am using the words fuzzy dark matter, ultralight axion dark matter, wave-like dark matter. There are a few others out there in the literature. I'm using those words interchangeably. There are contexts when you start to worry about interaction, like non-gravitational interactions, where different people are distinct about that. But I'm using. So yes, sorry. The short answer is yes.
I've got a question at the back.
So the bottom line is that masses below 10 to the minus 22 eV are ruled out?
They're ruled out as the only component of dark matter. Yeah.
Okay. Any further questions? Okay. Well, if not, let's thank Daniel again. Okay. So just before lunch, we've got a small number of poster talks. So as yesterday, if you could keep these to 2 minutes each, that's great. Okay, so our first talk is from Elisa Ferreira on unified superfluid dark sector.
Hello, good morning. So my name is Elisa Ferreira. I'm a postdoc fellow at the Max Planck Institute for Astrophysics. And my postdoc is about this work done in collaboration with Professor Robert Brunenberger that is here, and Justin Curry, and Guilherme Fransman. And in this work, we asked the question about what is the role of acceleration in the dark matter superfluid framework. And just to remind you what the dark matter superfluid is, it is another ultralight axion-like particle model, like Daniel said, but here we are working with EV masses, not 10 to the minus 22 EV. And the basic idea is that to solve the small-scale challenges of lambda CDM, we want this superfluid dark matter to condense on galactic scales, becoming a condensed state, so describing a different dynamics. So in galactic scales, you'll have the Mond dynamics, given effectively by this new degree of freedom of this condensate state. And outside galaxies, in cluster-like scales, you'll have a normal CDM dark matter. So this is done by using the physics of superfluidity. So you have collective effects responsible for this modification of the dynamics. And in this work, we asked the question, what happens cosmologically? So how do we describe this cosmology of this model? And for that, we had to make a better model of the superfluids. So superfluids are composed by atoms. So you have to take into account the structure, the internal structure of those atoms. So if you take this into account, you can have many different states in your superfluid, describing your superfluid. So now those states can interact. So the Lagrangian that describes now your cosmological evolution is going to be given by the P of x's that describe the superfluid dark matter, plus this cosine that is inherited from the interaction of the two components of the superfluid. So this model, it gives you the dark matter and the dark energy in a single framework. So we only have dark matter here, but the interaction between them gives you dark energy, as we can see here from the H over T plot. So we describe like lambda CDM evolution with a small change in the future. So this model is able to describe the late time acceleration, CDM, and also the small scale behavior of dark matter. We only have dark matter again, so the acceleration comes from the interaction within the superfluid. This model, it comes directly from condensed matter physics, so all these interactions are ubiquitous in condensed matter systems, so they need to be there to be considered as a superfluid. And we predict some observational signatures, like a different growth factor than lambda CDM, different for about 10%. So if you're interested, so ask me questions or come see my poster. Thank you.
Okay, thanks, Elisa. Okay, so next we've got Robert Reisker, and he's telling us again about axions.
Okay, hello, I'm Robert. I'm a postdoc at the Technion, and I present work done with some people from Heidelberg and Karlsruhe in collaboration. And thanks to Daniel, I don't have to tell you that much because he promoted my poster quite well already. So the project is about isocurvature bounds on axions in the post-inflationary scenario. So the idea is that the Purcell-Quinn symmetry is broken after inflation and not prior to, so that the axion has isocurvature fluctuations on the scale of the horizon when the symmetry is broken. And I will just give you the facts. If you want to see pretty pictures and have more information, please come to my poster and ask me. So the idea I already told you, and if the axion is sufficiently light, it can leave imprints in the large-scale structure and especially in the CMB power spectrum. And you can use this to put constraints on the axion mass, provided that all the dark matter is made out of this type of axions and via this production channel, so after inflation. And so what we are doing is we use the current CMB data and we forecast for the next generation of CMB and large-scale structure experiments, especially also for 21 centimeter cosmology. And what we find is that the axion mass can be constrained to be bigger than this with current data, so 10 to the minus 14 to 10 to the minus 16 electron volt. This depends on the exact formation model, and with stage 4 data, we can improve on this by roughly 1 to 2 orders of magnitude. So if you're interested in how this works and what axions are and how the Purkinje symmetry is broken after inflation, come to my poster. If the facts are enough, drink a coffee or go to another poster. Thank you.
Thanks, Robert. Have we got any more? Is that it? That's it, Christian.
Oh, I mixed it up. Sorry, thank you very much.
Okay, so let's thank both our poster speakers again. Okay, so we're going to break for lunch and we're going to reconvene at 2 o'clock. Is there anything the organisers want to say? No, we're good. Woohoo.